Hello everyone, welcome to Pushp Classes, a free online initiative for GATE, ESE and PSU एग्जाम। हम लोग एक बहुत ही इम्पोर्टेंट सब्जेक्ट दैट इज माइक्रो प्रोसेसर देख रहे थे, तो चले कंटिन्यू करते हैं। थैंक यू।
Now, coming to interrupts in 8085. So, what are interrupts? What are interrupts? Interrupt is an internal. It is an interrupt. It is an internal or external signal. It is an internal or external signal which may disturb or alter the sequence of execution of processor, which may disturb or alter the sequence of execution of a processor. Here it will be C, execution. Here it will be C, or I will write it again. Execution, execution, execution of processor. Suppose if we take an example of a cricket match. Suppose a cricket match is going on and a spectator or suppose a dog infiltrates the cricket pitch. Then what will happen? It will create an interrupt to the match. It will create an interrupt to the match, and the match will resume only when these interrupts are taken out of the cricket field. So we may call it as an external interrupt, which is coming from outside the cricket field. Now, if we talk about an internal interrupt, suppose a batsman gets hit by a bouncer and he requires medical attention, then then it is also a kind of interrupt, but that interrupt is taken inside the cricket field, so we call it as an internal interrupt. But in both the cases, there is disturbance and alteration in the sequence of execution of processor. So now coming to the classification of interrupts, interrupts can be classified as hardware and software interrupts, maskable and non-maskable interrupts, vectored and non-vector interrupts. So let's see what they are. So if we talk about the hardware interrupts, which are physically connected with the microprocessor, I can say it physically connected to microprocessor, physically connected, physically connected to microprocessor, these are called hardware interrupts. We have 5 types of hardware interrupts. First is the trap. This NMI is non-maskable interrupt. I will discuss it in coming part. And it is also known as RST 4.5, RST 4.5. Then we have RST 7.5, RST 6.5, RST 5.5, and INTR. INTR is interrupt request. INTR is interrupt request. INTR is interrupt request. INTR is interrupt request. So we have 5 types of hardware interrupts. Now coming to software interrupts, these are not physically connected with microprocessor. These are not physically connected with microprocessor, and there are 8 types of software interrupts. There are 8 types of software interrupt. There are 8 types of software interrupt. There are 8 types of software interrupt. There are 8 types of software interrupts, and they are denoted as RST N. They are denoted as RST where N is 0 to 7, where N is 0 to 7, where N is 0 to 7. This software interrupts, either they are used alone or they are used software interrupts, interrupts, software interrupts, software interrupts are either used alone in program, either used alone in a program, or they are used along with, or they are used along with INTR, that is interrupt request, or they are used along with INTR, that is interrupt request. Don't worry here. This all statements which I have written it, that I am going to discuss in details. See, there will not be any statement or word which is delivered by me without a proper explanation. So till now, just see what I have written and what I am briefing you. This all we will discuss in details in later part. Don't worry. So there are 8 types of software interrupt. It is represented as RSTN, where N is 0 to 7. To 0 to 7 means 8 interrupt, software interrupt. That is, we will get RST 1 or RST 6, similar like this way we will get, or we denote software interrupt. Fine. And they are used either alone in program or they are used with INTR. This also we will see when we will take up the instruction sets. Now coming to maskable and non-maskable interrupts. So what are maskable interrupts? Maskable interrupts are those interrupts which, when triggered, cannot be ignored by microprocessor. Maskable interrupt when triggered can't be ignored by microprocessor, And second one is non-maskable interrupt. These are interrupts which can be, or which can be ignored, by microprocessor, See, it is just like if you get a call from your home, that if your father or your mother calls you, then you sometimes ignore the call. So you can call it as a non-maskable interrupt. Sorry. I have written just reverse. Sorry. I have written it in just a reverse manner. So see, this is maskable and this is non-maskable. Maskable interrupts are those interrupts which can be ignored. Maskable, we can mask it. Interrupts which can be ignored, by microprocessor when triggered. And if we talk about non-maskable interrupt, then interrupt which can't be ignored, by microprocessor when triggered. So I was saying that if you get a call from your home, then sometimes you avoid the call. You doesn't receive it. So we can call it as a maskable interrupt. You can afford to avoid it. But if you get a call from your loved one, then you cannot afford to avoid it. You have to receive the call anyhow. So we can call it as a non-maskable interrupt. We can call it as a non-maskable interrupt. So out of all the interrupt, so out of all the interrupt, trap, out of all interrupt, trap is a kind of non-maskable interrupt. Trap is a kind of non-maskable interrupt. If trap is triggered, then it has to be processed. Then it has to be processed by the microprocessor. Okay, fine. Maskable and non-maskable interrupt. Now coming to vectored and non-vectored interrupt. Vectored, vectored interrupt. Interrupts which has a memory location. Interrupt, interrupt which has a memory location. Which has a memory location is known as vectored. And if we talk about non-vectored, then interrupt, which doesn't have any memory location, which doesn't have any memory location. So if we talk about all the interrupts, INTR, INTR is only one non-vectored interrupt. It is only one non-vectored interrupt. That's why I was telling you that sometimes INTR is used along with software interrupts, because see, what is the meaning of interrupt? Meaning of interrupt is that if interrupts are triggered, then I want the ongoing program to shift to some other address location and first complete operation of that address location and then come back to its routine work. Interrupt means if any ongoing program is going on, then I want to stop microprocessor for that ongoing work, and I want the attention of microprocessor to be shifted to somewhere else. So where the microprocessor will shift, will shift. For shifting microprocessor, we require a memory location. So for all the interrupts, we have a memory location. We have defined a memory location. But there's only one interrupt, INTR, interrupt request, which doesn't have a memory location. So whenever we use INTR, we use it along with RSTN. That is we use it along with software interrupt. So that again an address is defined that where the microprocessor has to switch its working, and how it is all done we will and how it is all done we will look into it in details. But for the time being, just know that INTR is a non-vectored interrupt. It is a non-vectored interrupt. Now, coming to a very important table, this single table is very important. You will have many information here. So first one is the priority. If we talk about the priority, if we talk about the priority of hardware interrupt, if we talk about the priority of hardware interrupt, then the priority is like this. First priority is trap or NMI or NMI or RST 4.5. Then second priority is of RST 7.5, then 6.5, then 5.5, and at last we have INTR. Okay, this priority is clear to you. Now if we talk about the type of trigger, see in digital we have studied that we have two type of trigger. We have studied in detail there that we have two type of trigger. One is the level trigger. This is called the level trigger, and this is known as the edge trigger. This is known as the as a trigger. This all we have studied it in details in digital. So if we talk about the type of trigger of interrupt, then if we talk about the trap, first one, then it is edge and level trigger both. It is edge and level trigger both. It is edge and level trigger both. If we talk about RST 7.5, then it is edge triggered. Then it is edge triggered. 6.5 is level triggered, 5.5 is level triggered, INTR is level triggered. This type of questions you most often get to see in ESE exam or in PSU exam. So say it nicely. So now why trap is edge and level triggered? 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 See, trap is a non-maskable interrupt. Means once it is triggered, it has to be attended by microprocessor. So that's why it is an edge triggered, because its priority is high. Because its priority is high. But see, there is a chance that instead of actual signal, there is a noise. There is a noise which is triggering this trap. So, just because of noise, my whole processing of microprocessor will get interrupted. Because it is a trap, it has to be attended by microprocessor. So, to avoid this, we use level trigger. To avoid this, we use level trigger. That's why for triggering of trap, we require 3 clock pulse. That's why for triggering of trap, we require 3 clock pulse, because noise doesn't last for long. Noise will last for just 1 clock pulse and then it will get lowered. So for double confirmation, we are using so for double confirmation that the signal which is triggering the trap is not noise and it is actually our main signal, we are using 3 clock pulse. So that's why the type of triggering used in trap is both edge and level triggered. Edge just because its priority is high, level just because we want to differentiate between input signal and noise. We want to differentiate between input signal and noise. Now coming to the address location, as I was saying that whenever we interrupt a microprocessor, then we want it to switch to some other memory location where it has to perform another function. So where it will be switched. So if suppose if trap is triggered, then microprocessor will switch it will automatically switch to memory location 0024H. Now, if RST 7.5 is triggered, it will automatically switch to 003CH. If 6.5 is triggered, it will switch to 0034H. If 5.5 is triggered, it will switch to 002CH. For INTR, we don't have any memory location. Why? Because INTR is non-vectored. It is non-vectored interrupt. It is non-vectored interrupt. All these are vectored interrupt. All these are vectored interrupt. If we talk about trap, then it is non-maskable interrupt. And all these are maskable interrupt. So you can see that so many information you are going to get from a single slide, and this slide is very important for your exam point of view. So what we discussed? First we discussed the priority of interrupts. It is in this order. Then we saw the type of trigger which are used for each interrupt. Then we saw the address location of each interrupt. Now, coming to vector addressing of software interrupt. Now coming to vector addressing. Now coming to vector addressing. Now coming to vector addressing. vector addressing of software interrupt, vector addressing of software interrupt, vector addressing of software interrupt. So what it is? See, in the hardware interrupts, we saw that what are the address location of each hardware interrupts? What are the address location of each hardware interrupts? So similarly, if a software interrupt is triggered, then where will the microprocessor shift? In which address location? In which address location the microprocessor will shift? In which address location the microprocessor will shift? 0 to 7. So see what is the process. Suppose uh, we have RST 5. Suppose we have RST 5. We have RST 5. Suppose we have RST 5. So step 1 is, step 1 is we will multiply 5 with 8. We will multiply 5 with 8. This is 40. And this is in decimal. This is in decimal. This is in decimal. Now step 2. Now step 2. Now we will convert this decimal to hexadecimal. Now we will convert this decimal to hexadecimal. So how it can be converted? 16 to 8. So its address will be, it goes this side, 002 at 28H. So this will be the address. This will be the address location for RST5. This will be the address location for RST5. So suppose we are given any software interrupt like RST5 or anything, we will first multiply it by 8. We will first multiply it by 8. Then the value which we will get it in decimal. The value which we will get it in decimal. And then we will convert this decimal into hexadecimal. We will convert this decimal into hexadecimal, and this will be our address location. This will be our address location. Now suppose if we take one more example. Suppose we have RST 7.5. So what is my step 1? My step 1 is multiplying it by 8. We will get something like what? 60. 60 is in decimal. Now we will convert it into hexadecimal. 48, 12. Sorry, not 48. Not 48. This will be 3, 12. Move this side. So 003CH. So this is the memory location of my software interrupt RST 7.5. See, this, here I have just taken two example. When we will come into instruction set and when we will solve a number of programs, then there we will again see this all in details, and you will get an idea that how it is working, and you will get an idea of how it is working. So this was all about. So this was all about our interrupts. We have seen different categories of interrupt, different classification of interrupt, and that too in details. Now coming to internal architecture of microprocessor. So in earlier classes, we have seen pin diagram of microprocessor. And now we will look into internal architecture. Of a microprocessor. Internal architecture of microprocessor. So let's see each part one by one. So this is my timing and control. This is my timing and control part. or we can say timing and control unit. This is my timing and control unit. Here you can see that x1 and x2 are connected. X1 and x2 are connected. We have already learned about x1 and x2, and in between x1 and x2 there is a crystal oscillator. In between x1 and x2 there is a crystal oscillator which generates reference frequency. Then we have seen clock out, we have seen ready, which is used to interface with slow peripheral devices. Then we have seen read bar. Here bar is not shown, but it is generally, but it is not generally, it is bar only. Read bar, write bar. Then we have seen the functions of ALE, then S0, S1 are our status pin. S0, S1 are our status pin. Then we have input output memory bar. Then we have input output memory bar pin. Then we have hold and HLDA, which is used when a DMA operation is taking place. Then we have hold and HLDA, which comes into picture when DMA operation is taking place. Then we have reset in pin. It is used to reset microprocessor. In our earlier class, where I taught you details of reset pin, there I missed one point, that whenever reset pin is operated, then microprocessor gets resetted. And content of program counter changes to 0000H. Then content of program counter changes to 0000H. This is an important objective question. Resetting. I taught you earlier, but I missed this point, that what will be the value of program counter when reset button is pressed. Now we have reset out. Now we have reset out pin. So this was all about our timing and control unit. Now here we can see that here is our higher order address bus. This is our higher order address bus. This is our lower order address bus, which also acts like a data bus. Here we have address buffer. Here we have data address buffer. That is whenever data flows from microprocessor to input output devices and memory. That is whenever data flows from microprocessor to peripheral devices, or from peripheral devices to microprocessor. Then first data comes here. And then it goes either inside microprocessor, or it goes either outside microprocessor, Then here we have different types of registers. See this part we have already dealt in details. The timing and control unit. Here this address buses, data buses, this also we have dealt in details. This part we are going to deal in detail. This part there's nothing much to discuss in this part, but still we will look in our upcoming topics. Then we will discuss in details flag registers. We will discuss ALU. When we will start our arithmetic instructions. Then here are our temporary registers. I will tell you what is the significance of this temporary registers. Here is our accumulator. Very important register. So here we can see that this is the register set. Here we have temporary resistors W and Z. Here we have temporary resistors. Here we have temporary resistors W and Z. We will discuss this. What is the significance of this temporary resistors? Then we have resistors B, C, D, E, H, L, B, D, H. As if we talk now, see, uh, we have six type of resistors. We have six types of resistors like B, either B, C, D, E, H, L. If we take it independently, then they form 8-bit resistors. But if we use them as pair, then they form a resistors pair, and it is a 16-bit resistor pair. And it is a 16-bit resistor pair BC, DE, HL. Then we have stack pointer. Then we have a stack pointer. We will discuss it in details when we will study about the instructions push and pop. When we will study about the instructions push and pop. Then we have program counter. Very important register. This is a very important register. It is a 16 stack pointer is also 16-bit register. Program counter is also 16-bit register. Very important register. Then we have increment, decrement, and address latch. Now ALU, we all know the basic functionality of ALU. Then we have flag registers. We will see it in detail. It is also a 8-bit register. It is also an 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 8-bit register. Now, what all we have in the upper portion? In the upper portion, we are having interrupt controller. Here we are having all types of interrupts. Here we are having all types of interrupts. Here we are having all types of interrupts. Here we are having all type of interrupts. Then here we have this may be not visible to you, so I can write it. This part is the serial controller. 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 Here we have SID, SOD, serial input data, serial output data. This both we will discuss in detail when we will discuss SIM and RIM instruction. When we will discuss SIM and RIM instruction. When we will discuss SIM and RIM instruction. So this is our internal architecture of 8085 microprocessor. This is our internal architecture of 8085 microprocessor, in which you can see that each sub-modules are interconnected with each other. Each modules and sub-modules are interconnected with each other through internal buses, through internal buses, through internal buses through internal buses, through internal buses. So this was all about the internal architecture of 8085 microprocessor. I have given, it is not all about, I have just given you an overview. I have just given you an overview of internal architecture of 8085 microprocessor. Now we will discuss each new modules and each new sub modules which we have encountered here. We will discuss each one by one, and that too in detail. See, when we were discussing interrupts, then I missed a small part. I missed a small part, so I will cover that. So I will cover that also. See, these are our interrupts. See, these are our interrupts. See, these are our interrupts. These are our interrupts. I can say it like trap, RST 7.5, RST 6.5, RST 5.5, and INTR and INTR. INTR, I told you, interrupt request. This all are input to microprocessors. 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 Here I left a important pin, that is INTA. Here I left a important pin, that is INTA. INTA is interrupt acknowledgement. INTA is interrupt. INTA is interrupt acknowledgement. Interrupt acknowledgement, acknowledgement, interrupt acknowledgement, interrupt acknowledgement, and INTA. And this is the first. It is full form of INTA, interrupt acknowledgement, interrupt acknowledgement. Second one, it is output pin. It is output pin. It is output pin. It is output pin from microprocessor. It is output pin from microprocessor. And third one is, it is always associated, always always associated with INTR, always associated, always associated with INTR. It is always associated with INTR. That is, whenever INTR is triggered, whenever INTR is triggered, then 8085 microprocessor sends an output pin for acknowledgement of INTR. It sends an output pin for acknowledgement of INTR, and it is known as INTA, that is interrupt acknowledgement. That is interrupt acknowledgement. So I hope this part is clear. I missed it when I discussed the topic of interrupt, but now I have covered it. So see, here I told you that when we discussed reset in pin, when we discussed reset in pin, then at that time I missed a small part, and that was whenever reset pin is operated, whenever reset pin is operated, then what will be the status of program counter? What will be the status of program counter? What will be the status of program counter? Then I told you that program counter value or address will change to 0000h. It will change to 0000h. And another topic which I missed was when I discussed interrupts, I missed INTA. So here I have dealt it with the details. So full form of INTA is interrupt acknowledgement. It is a output pin from microprocessor. It is a output pin from microprocessor, and it is always associated with INTR, that is a interrupt request. It is always associated with INTR, that is interrupt request. That is whenever INTR is triggered, whenever INTR is triggered, then microprocessor sends an output signal. Microprocessor sends an output signal INTA as an acknowledgement, as an acknowledgement of INTR, as an acknowledgement of INTR, as an acknowledgement of INTR. So fine. So now again coming back to the internal architecture of microprocessor. So now again coming back to the internal architecture of microprocessor. So it is divided into 5 functional unit. It is divided into 5 functional unit. We have seen this earlier also, but now we have categorized it. We have 5 functional unit. First one is the register unit. Second one is the ALU. Third one is the timing and control unit. Then we have interrupt control unit. Then we have serial input output control unit. I told you that this part we will discuss when we will take up RIM and SIM instruction. When we will take up RIM and SIM instruction. Interrupt control unit, it is already over. It is already over. Timing and control unit, it is also over. It is also over. So now in this part we will study register unit and ALU. We will study register unit and ALU. Now you can see that we have almost come into the starting of our instructions. Just after the discussion this two part, thus the just after discussing this register units and ALU, I am going to enter into our most important part, and that is discussion or instruction set. That is discussion or instruction set. So we will look into this two part. We will look into this two part. So if we come into register unit, so if we come into register unit, so if we come into register unit, then register unit is divided into two part. Register unit is divided into two part. Register unit is divided into two part. First is the general purpose register. 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 And the second one is special purpose register. Second one is the special purpose register. Second one is the special purpose register. Fine. In general purpose register, we have six registers. We have six registers. In general purpose registers, we have six registers. And what are those six instruction registers? They are B, C, D, E, H, L. These are our six registers. These are our six general purpose registers, and all these registers are of 8-bit. All these registers are of 8-bit. All these registers are of 8-bit. But we can use these registers as register pairs. We can use these registers as registers pair, and when we are using these registers, when we are using this general purpose registers as register pair, then it becomes 16-bit registers. 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 Now coming to special purpose register. Now coming to special purpose register. Here we have accumulator. Here we have accumulator. Here we have accumulator, program counter, stack pointer, flag register, instruction register, instruction register, instruction register, instruction register, instruction register, instruction register. So in special purpose registers, we are having accumulator, program counter, stack pointer register, flag register, and instruction register, and instruction register, and instruction register. So let's see each type of these registers one by one, and we will try to find out, and we will try to see what functions and what significance these registers hold. Now, in general purpose register, out of this three register pair, HL register pair holds much of a significance. HL register pair holds much of a significance. So we will discuss the significance of HL. register pair. We will discuss significance of HL register pair. We will discuss significance of HL register pair. So, HL register pair is also known as default memory pointer. HL register pair is also known as default memory pointer. It is also known as default memory pointer. It is also known as default memory pointer. So if you get an objective question that which register pair is known as default memory pointer, which register pair is known as default register memory pointer, so you will say that HL register pair is also known as default memory pointer, is also known as default memory pointer. Now see, let's see how it works. Suppose we have a microprocessor. Suppose we have a microprocessor. Suppose we have a HL pair. Suppose we have a HL pair, and content of HL pair is, suppose we have this 6000. 6000. This all are in hexadecimal because HL pair is 16-bit register. 16-bit register. Now suppose we have a memory. Now suppose we have a memory connected with this microprocessor. Suppose we have a memory connected with this microprocessor, and here with one of the memory location we are having 6000H, and the data in that memory location is suppose 20H. One of the memory location, that is address of one of the memory location is 6000H, and the data here is 20H. Data here is 20H. Now suppose you are given an instruction. Suppose you are given an instruction move B comma M. You are given an instruction move B comma M. Then by this instruction you know that you have to copy data into B. You have to copy data into B. But then you will have two questions. You will have two questions. You will have two unanswered questions in this instruction. This instruction is having two unanswered questions. First one, what is the data? What is the data? You don't know the value of data. What is the data? You don't know the value of data. Second is, where is the data? Second is, where is the data? You don't know the location of data also. You don't know the location of data also. So if you don't know the location as well as you don't know the value of data, then how you are going to copy some imaginary thing into register B? How you are going to copy some imaginary thing into register B? So these two questions are solved or answered by this register, which is also known as memory register. This is also known as memory register. This is also known as memory register M. M is also known as memory register. And now see how our both questions are answered. How our both questions are answered. This M means that data is present at an address. Data is present at an address which is the content of HL pair. Which is the content of HL pair. Which is the content of HL pair. This memory register always point HL register. this memory register always point HL register pair. This memory register always point HL register pair, and in this instruction it is saying that data is present at a memory location. Data is present. Data, this is the data. It is present at a memory location. It is present at a memory location, and that memory location is the address of HL pair, and that memory location is the address of HL pair. So not the address, it is the content of HL pair. Means it is signifying that we have a data 20H, and address or location of this data is the content of HL pair, is the content of HL pair. Now you can see that content of HL pair is 6000. So using this content of HL pair, using this content of HL pair, now this content will become address, this content will become address, and now this address will come to the memory, this address will come to the memory, and this memory location will get highlighted, this memory location will get highlighted, and this data 20H will be copied and brought back to register B. It will be copied and brought back to register B. So always keep in mind that memory register always point HL pair. Memory register always point HL pair. Now suppose we have a instruction like this. Now suppose we have an instruction like this. So from this instruction we know that we have to copy content of B into this, Now what this is, we don't know. What this is, we don't know. We don't know where we have to copy data of B. So this is answered by my memory register. This is answered by my memory register. I told you that memory register always point HL register pair. Memory register always point my HL register pair. So it is saying that the data of B will be copied, Where it will be copied? It will be copied at the address location, which is content of HL pair. So what is the content of HL pair? Content of HL pair is 6000H, and now this content of HL pair will act as an address, and through address and data bus, this address will be highlighted. This location in the memory, will be highlighted, and our data of B, suppose it is 20H, it will be copied here. So I think now it is clear to you. HL register pair is default memory pointer. We can see that content of HL pair is pointing the memory. And how this operation is taking place? This operation is taking place through a memory register. This operation is taking place through a memory location. That is, HL register pair is a default memory pointer, and this operation is taking place through memory register. That is, memory register always points HL pair. So this was the significance. Of our HL register pair. See, these two instructions which I have taken, I have just taken these two instructions to give an idea of the significance which HL register pair holds. Where I will discuss all these instructions. When I will take the instruction set lectures. and there we are going to see all these instructions in details. There we are going to see all these instructions in details, and you will really enjoy it. You will really feel how these instructions are executed by microprocessor. Everything will be opened in front of you. But here I have just taken a small but here I have just used this two instruction in a very small way, just to brief you the functionality of register pair as a default memory pointer. So don't think that in that we are going to learn instruction all the instructions in this way only, in this short way only. We are going to see it in details. You will just enjoy it. You will just enjoy that lectures, and I don't think that you will find a similar lecture on instruction set anywhere else. So just wait, and we will discuss everything in details. So this was all about our general purpose register. We have 6 registers: B, C, D, E, H, L. If we use them independently, then all are of 8 bit, and when we use them as a pair, then it is of 16 bit. And for that, HL pair is of holds much significance. And what is the significance and how it works, we have discussed it in details here. Now coming to the special purpose register. Coming to the special purpose register, so first is the accumulator. See, accumulator we can call it as a multi-purpose register. See, accumulator we can call it as a multi-purpose register because it has functionality of general purpose also, it has functionality of special purpose also. But in exam, if you get a question on accumulator, and if there is no option of multi-purpose register, then you will take it for general purpose register. You will not take it for you will take it for special purpose register, and you will not take it for general purpose register. So what I am saying is that accumulator is a kind of multi-purpose register which has functionality of general purpose register as well as special purpose register. But in exam, if you are asked a question and in option there is no multi-purpose register, so you will go for special purpose register. So you will go for special purpose register. So now coming to accumulator. Here I am giving you just a brief idea of all the register, so that you will get a feel of it. And when we will start our instruction set, then you will not think these instructions as an alien. These instructions will not look like an alien to you. You will just have a basic idea that what all these instructions, these registers do. So accumulator, it is 8 bit. It is a 8-bit multi-purpose register. It is 8-bit multi-purpose register. It is 8-bit multi-purpose register. All arithmetic and logical operation. All arithmetic and logical. All arithmetic and logical operation. All arithmetic and logical operation are performed using accumulator. Are performed using accumulator. So accumulator is a very important register. When we will discuss instruction set, then you will see that how important this accumulator is. You will find a accumulator in each and every instruction. If you will develop a program, then you will see that you will find accumulator in each and every instructions, and it has a role to play everywhere in your program. So it is a 8-bit multi-purpose register. All arithmetic and logical operations are performed using accumulator. Now coming to another special purpose register. It is program counter. It is a program counter. This is also very important register. It is 16-bit register. It is 16-bit register which holds address address of next instruction to be executed if you will see the previous year gate or previous year ESE or PSU exam, you will see that so many times this line, so many times questions are asked based on only this line. So many times questions are asked based on only this line. So you can determine that how important this register is. And in reality also it is very important. Register because it maintains it maintains direction and flow of program. It maintains direction and flow of program. So what it is? It is 16-bit register. It is 16-bit register which holds address of next instruction to be executed. Address of next instruction to be executed. Suppose we have an instruction like this. Suppose we have memory location this. Here we are having one instruction, move A comma B. Then suppose we have another instruction, MVI A02H. Then we have another instruction, move A comma C. Now suppose microprocessor is executing this instruction. Then if anyone asks you that what will be the status of program counter, then you will say that status of program counter will be 2001H. That is, it will always point address of next instruction which is going to be executed. It will always point address of next instruction which is going to be executed. Now suppose microprocessor is executing this instruction, then what will be value of program counter? The program counter will point to 002H. That is address of next instruction to be executed by microprocessor. It always highlight or points or holds address of next instruction to be executed by microprocessor. And by doing what it is doing, by doing it is maintaining a direction, it is maintaining a flow of program, it is maintaining a direction, it is maintaining a flow of program. That is it is giving direction to microprocessor that in which order it has to proceed. That it is given direction to microprocessor that in which order it has to proceed. Suppose there are five friends, and these five friends are walking through a tunnel. These five friends are walking through a tunnel, and only one of the friends is having a torch with him. Only one person out of these five persons are having torch with him or her. Then see, the person who is having the torch, he will always be the first person in the tunnel. The person with the torch will be the first person in the tunnel, and the rest all will follow him. And so this person is providing a direction, and it is providing a path for other persons to follow. So same this work is done by program counter in microprocessor. This work is done by program counter. This work is done by program counter in microprocessor. So this was all about program counter. Now coming to another special purpose register, that is instruction register. That is instruction. That is instruction register. Instruction register. So it is 8-bit register. It is 8-bit register which holds. It is 8-bit register which holds. It is 8-bit registers. See, while writing, I write very quickly, so the handwriting will be uh, not so beautiful for you, but you can refer my notes. You can refer my complete notes. There the handwriting will be very beautiful, and so you can refer that. But here, just to make up the time, I write little quickly, but still I make sure that you get an understanding of what I am writing. So I think that you can understand it here, that it is 8-bit register which holds opcode of any instruction, which hold opcode of any instruction, which hold opcode of any instruction. See, suppose here we have a microprocessor. Here we have a microprocessor. Here we have instruction register. Here we have instruction register, and it is connected with a decoder. 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 So see, suppose we have an instruction like, suppose we have this instruction, move A comma B. Move A comma B. See, this we have studied in our earlier lecture, that this is known as mnemonics. This is known as mnemonics, which is not understood by microprocessor. It is understood only by programmer. It is not understood by microprocessor. So we have an equivalent hexadecimal code for it. Suppose it is XXH. Okay. This hexadecimal code is not much of significance to us. We don't have to remember it. Questions are not asked from too far to find out that what will be the what will be the code of any mnemonics. It is mainly for programmer. Whenever a programmer develops a program, then when they feed the program into the microprocessor, then they just refer the codes, and they just feed that code into the microprocessor. It is not important for exam point of view. So this is our mnemonics, which is not understood by microprocessor, because microprocessor only understand binary terms. So we have converted it into a code, into a hexadecimal code, and this hexadecimal code is known as the opcode. This hexadecimal code is known as the opcode. This hexadecimal code is known as the opcode. So the first work, whenever a program is executed, or you can say whenever an instruction is executed by microprocessor, whenever an instruction is executed by microprocessor, so the first work it does, the first operation it does is that it read this opcode from the memory. It read this opcode from the memory, which is known as the opcode fetch, which is known as the opcode fetch. This opcode comes into our instruction register. This opcode comes into our instruction register, and then it goes to decoder, where the instruction is decoded. Where the instruction is decoded. So now after decoding it, microprocessor knows that what it has to do. That is, after decoding this, microprocessor knows that it has to copy data of B into A. So this is the working of instruction register, that is it holds opcode and then it transfers the opcode to decoder and it is then decoded. See this opcode fetch, how microprocessor is fetching this opcode fetch, how the microprocessor is fetching this opcode. This all we are going to deal in the details when we will start our instruction set. So don't put your much brain here. You just have a basic understanding that what is the function of instruction register, that is it holds opcode which is fetched by the microprocessor from memory, and then it is given to decoder for decoding. And what is opcode? It is hexadecimal equivalent of mnemonics. It is hexadecimal equivalent of mnemonics. Now coming to another important instruction, that is stack pointer. Now coming to another important instruction. Now coming to another important instruction. That is now coming to another important instruction, that is stack pointer. So it is a 16-bit register. It is 16-bit register. It is 16-bit register which points address of data which is at top of stack. So it is a 16-bit register. It is a 16-bit register which points address of data, which is at top of the stack, Or we can also say that it points to data at top of stack. It points to data at top of stack. So stack pointer is 16-bit register which points address of data which is at top of the stack, or it points to data at top of the stack. See, suppose we are having a stack like this. Here we are having data and here we are not having any data. So this is the data which is top of the stack. And the address of this data is 2000H, and this is pointed by stack pointer. That is, value of stack pointer will be 2000H. This we will discuss in details when we will discuss push and pop instruction. Stack pointer is used in push and pop instruction. We will discuss it in details there when we will discuss the push and pop instruction. Okay, so this was about our stack pointer. Now next is a flag register. This register is very important whenever any arithmetic and logical operation takes place. Whenever any arithmetic and logical operation takes place, then this register comes into picture. It is a 8-bit register. It is 8-bit register. There are 5 flags. There are 5 flags which give status. which give status, which give status, which give status after any arithmetic and logical operation, after any arithmetic or logical operation, or logical operation, or logical operation. So it is 8-bit register. There are total 5 flags which give status after any arithmetic and logical operation is executed, is executed, is executed, is executed. So let's see what are the 5 flags. So let's see what are the 5 flags. Let we have an 8-bit register. 1, 2, 3, 4, 5, 6, 7, and 8. So first is the sign flag. First is the sign flag. Then comes the zero flag. Then comes the zero flag. Then the auxiliary carry. Then auxiliary carry. Then comes our parity flag. Then comes our parity flag. And then comes our carry flag. And then comes our carry flag. So as I told you that flag register is a 8-bit register, but we have only 5 flags: sign flag, zero flag, auxiliary carry, parity, and carry flag. So remaining this 3 bits, we treat it as don't care. We treat it as don't care. We treat it as don't care. So what are the flags? We have sign flags. We have sign flag. Then we have zero flag. Then we have zero flag. Then auxiliary carry. Auxiliary carry flag. Then we have parity flag. Then we have parity flag. And then we have carry flag. And then we have carry flag. Position of all these flags holds much important. Position of all these flags holds much importance. Holds much importance. So let's see. This is the sign flag is at D7 bit of flag register. It is at D6 bit. It is at D4 bit. It is at D2 bit, and it is at D0 bit. Positioning of or position of flags holds much of an importance. So we should know that where all these flags are placed into the 8-bit register of flag register, into 8-bit register of flag register. So now let discuss each flag one by one. So now let discuss each flag. So now let discuss each flag one by one. Now coming to first flag, that is sign flag. Coming to first flag, that is sign flag. So there are two states, 0 and 1. There are two states, 0 and 1. 0 means positive result. 0 means positive result. 1 means negative result. 1 means negative result. Suppose we take an example. Suppose we take an example. Suppose it is example 1. Let content of accumulator. Let Content of accumulator is something like this. Content of accumulator is something like this. This is example 1. And if we take another example, example 2, then let the content of accumulator is something like this. Content of accumulator is something like this. Here, value of D7 bit. Here, value of D7 bit. This is our D7 bit. This is our D7 bit. So here if I talk, then the value of D7 bit is 0. Value of D7 bit is 0. Here value of D7 bit is 1. Now we very well know that sign flag is represented by D7 bit. Sign flag is represented by D7 bit. So here the value of sign flag is 0 and here the value of sign flag is 1. That is, this value of accumulator, that is this value of accumulator signifies positive result. It signifies positive result. Whatever may be the value, it will come in the form of this plus 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 9 plus 8. It will come in this value. And here as the value of sign flag is 1, so it represent negative result. It represent negative result. That is, it will come in the form of -9, -8, so on. I'm not saying that if you will convert this into decimal, you will get this. I'm just taking an example. So see, here sign flag doesn't care that whether operation is signed operation or unsigned operation. That the programmer has to take care on their own. For sign flag, the thing which matters is the D7 bit. If the D7 bit is 0, then it means result is positive. If the D7 bit is 1, then it means the result is negative. Then it means the result is negative. See, while explaining the concept of all the flags, I am going to take content of accumulator as a reference. I am going to take content of accumulator as a reference. And I am doing so because in almost all ALU operation, mark my word, I am saying almost. I am saying almost. I am not saying always. I am not saying always. I am saying that in almost all ALU operations, final result is stored as content of accumulator. Final result is stored as a content of accumulator. So the status of sign flag is concluded from the content of accumulator. But still there are some instructions like increment instruction, decrement instruction, where after ALU operation the content is not saved as content of accumulator, whereas the result is saved within the register itself. The result is saved within the register itself, and in that case the value of sign flag depends upon the content of that register. It depends upon the content of that register after ALU operation. But as in most of the cases, content of accumulator, based on the content of accumulator, we can find out the status of different flags. That's why while briefing you the concept of flags, I will take content of accumulator as a reference. I will take content of accumulator as a reference. Now, coming to second flag. Now coming to second flag, and that is zero flag. Now coming to second flag, and that is zero flag. It also has two states, 1 and 0. When we will get 1? When content of accumulator is 0. When content of accumulator is 0, or bits all bits from D0 to D7 of accumulator is 0, then a 0 flag is set. Then 0 flag is set. And when we will get 0? When at least one bit is non-zero. If at least one bit from D0 to D7 is non-zero, then the 0 flag is reset. At least one bit from D0 to D7 is non-zero, that is content of accumulator. If content of accumulator is 0, then 0 flag is set. If content of accumulator is non-zero, then 0 flag is not set. Then 0 flag is. Now coming to next instruction, that is auxiliary carry. Coming to next instruction, that is auxiliary carry flag. See, if there is a carry out, if there is a carry out from D3 bit to D4 bit, or we can write, and we can also say it as from lower nibble. Group of 4 bit is known as a nibble. From lower nibble to higher nibble. If there is a carry out from D3 bit to D4 bit, or from a lower nibble to higher nibble, then auxiliary carry is set. Otherwise auxiliary carry is not set. Otherwise auxiliary carry is not set. Suppose we have an example, like suppose we have an example like this. We are doing addition. Then it will come this. Now this, here you will have a carry. Here you will have a carry. So this is my lower nibble. See, this is my lower nibble. This is my lower nibble. This is my higher nibble. This is my higher nibble. Or we can say this is our D3 bit. And this one is our D4 bit. This one is our D4 bit. And there is a carry. And there is a carry. There is a carry. Then in this case, auxiliary carry will be 1. In this case, auxiliary carry will be 1. Now, coming to next flag, that is parity flag. So we can define it as if number of ones number of ones in content of accumulator, in content of accumulator, in content of accumulator is even, is even, is even, then parity flag, then parity flag is set, then parity flag is set. If number of 1 in content of accumulator is even, then parity flag is set. And if number of 1 in content of accumulator is odd, then parity flag is not set. So we can write otherwise parity flag is not set if number of 1, if number of 1 in content of accumulator, in content of accumulator is odd, is odd, is odd, is odd. So this is about the parity flag. Suppose we have an example. Suppose we have an example. If content of accumulator is this, then say what will be the status of parity flag? What will be the status of parity flag? What will be the status of parity flag? Here you will say that sir there is no one here. So we cannot determine. So no one means 0, 1, and 0 is also considered as an even number. So here the parity flag will be set. Here parity flag, here parity flag will be set. Here parity flag will be set. For all this value 0, 0, 1, 1, 2, 2, 3, 3, so on, FF. For all this value, if content of accumulator or any resistor which is determining parity flag, if their content is 0, 0, 1, 1, 2, 2, 3, 3, so on FF, then parity flag is always set for this. Keep it in mind. Parity flag is always set for this. It's a kind of shortcut. It's a kind of shortcut. So now coming to the next and the last flag, that is carry flag. Coming to the last flag, carry flag. If there's a carry, if there's a carry from D7 bit, from D7 bit of accumulator or accumulator or any resistor as such on which flags are status of flag is dependent, then carry flag is set, otherwise carry flag is not set, otherwise carry flag is not set. If there's a carry from D7 bit of accumulator, then carry flag is set, otherwise carry flag is not set. Now let's take a question. Now let's take a question on flag. Suppose content of accumulator is 76H and content of resistor B is 8AH. 8AH. We have to do addition. We have to do addition and the final result will be saved in accumulator. Final result will be saved in accumulator. So what will be my result? So what will be my result? See 6 plus A, 16, 16 we say 1, 0, 1, 0. Here we have a carry. Here we have a carry. 8, 8, this 0. And again here we have a carry. Again here we have a carry. So see, what will be the status of flag register? What will be the status of flag register? What will be the status of flag register? See, if we start with the sign flag, then we can see here that it is 0. It is 0. The last bit, if we will expand it, what we will get? We will get something like this. If we will expand it, we will get something like this. So the value of sign flag, is 0. The value of sign flag is 0. Now, if we talk about the 0 flag, then see, 0 flag will be set because content of accumulator is 0. 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 Now, if we talk about the auxiliary carry, then we can see that there is a carry from lower nibble to upper nibble. There is a carry from lower nibble to upper nibble. So auxiliary carry will be set. Now, if we talk about the parity, then 0 0, I told you earlier, for 0 0 parity will be set. And if we talk about the carry, then from the D7 bit there is a carry, so this will also be set. So this will be my status of flag registers. And if someone asks you that find the value of flag register, then we will put here 0 0. So here also 0. Then we will convert it into hexadecimal. Then we will convert it into hexadecimal. And from there we will find the answer. Here then we will convert it into hexadecimal, and we will get answer as 55H. If someone asks you that what is the value of flag register, then it will be 55H. See, here I have directly solved it. There's another method, but it will take some time. You first convert it into binary. And then again, when you will add it, then again you will get the same answer. And if you will find the status of flags, you will get the same result. But this all things we have discussed in digital, so I am not going to discuss all these things in microprocessor. We have discussed it in details when we have studied digital portion. Now suppose we take another question. Here content of accumulator is 58H, content of C is 95H. We will again do AND operation, addition, and we have to find that what will be the content of accumulator. So see, add it. 8 plus 5, 13. In hexadecimal, 13 is represented as D. Here 9 and 5, 14. In hexadecimal, 14 is represented as E. Now see, if we convert it into binary, what we will get? We will get something like this. Now what will be the status of our flags? What will be the status of our flags? So see, sign flag, D7 bit is 1, so sign flag 1. 0 flag, content of accumulator is not 0, so it will not be set, it will be 0. Auxiliary carry, see, is there any carry from lower nibble to upper nibble? No, there is no carry, so it will come as 0. Now parity, count number of ones, 3, 6. Parity is set. Now carry, is there any carry from the D7 bit or from the upper higher nibble or from the higher nibble? No, it is 0. So this will be my content of flag register. This will be my content of flag register. So by this way, we find out the status of flag, and similarly, we find out the status of our flag registers. We find out the status of our flag registers. Now there is one another register which we call as PSW. Its full form is program status word. Program status word. It is not a separate register. It is not a separate register. What we have done is that we have combined A and F. We have combined A and F. A is the accumulator and F is the flag register. F is a flag register. So we can say that PSW is a 16-bit register. It is a 16-bit register and it is combination and it is combination and it is combination of accumulator and flag register and flag register. So PSW is not a separate register as such. It is just a combination of accumulator and flag register. Suppose we have a value of accumulator as 05H and value of flag register is suppose 0AH. Then what will be the value of PSW? Value of PSW will be 050AH. In PSW, the higher nibble is the content of accumulator. Lower nibble is the content of flag register. Lower nibble is the content of flag register. Now coming to one another type of instruction, it is known as not instruction, register. It is known as temporary register. It is known as temporary register. We have two 8-bit registers W and Z. It is combined together to form a temporary register. We have two 8-bit registers W and Z. Here we have combined both to form a 16-bit temporary register. To form a 16-bit temporary register, this register is not accessible to user. This register is not accessible to user. It is used in some specific instruction. It is used in some specific instruction. Here I am not going to tell you that in which instructions we use this temporary register, but when we will take up the instruction set session, there I will discuss it in details. So we can write it. It is 16-bit register. It is 16-bit register formed. It is a 16-bit. It is a 16-bit register formed by combining two 8-bit registers. Two 8-bit registers. Two 8-bit registers W and Z. Two 8-bit registers W and Z. Temporary registers are used during specific instruction execution. And one more thing we can write, it is not accessible to user. It is not accessible to user, or I can say programmer, or I can say programmer. So this was all about the different types of resistors. This was all about different types of resistors, where we have seen general purpose resistor, special purpose resistors, flag resistors, and some other type of resistors like PSW and temporary resistors. So this was all about our different types of resistors. Now, before starting instruction set, there are two small point which I need to discuss. First is the instruction format. First is the instruction format. First is the instruction. First is the instruction format. First is the instruction format. So instruction format is always like this. This is my opcode. This is my opcode, and this is my operands, and this is my operands. This is my opcode, and this is my operands. Opcode means operation code. Opcode means operation code. It mainly signifies that what execution we want from microprocessor. It mainly signifies what execution we want from the microprocessor. Suppose we have a instruction like move a comma b, move a comma b. Here move is the opcode. Here move is the opcode. Here we want to move data of b to a, data of b to a, data of b to a. So move is the opcode, means what we want is signified by move, that is opcode. Like similarly, if we have something like this, move immediate, a comma 8-bit data. So here move immediate is my opcode, because by this I am instructing microprocessor, to transfer this 8-bit data to accumulator, transfer or copy this 8-bit data to accumulator. So this is my opcode, and these are my operands. These are my operands on which opcode is executing. These are my operands. So operands may be 8-bit data, operands may be 8-bit data, it may be 16-bit data, it may be 16-bit address, it may be 16-bit address, it may be simply registers, it may be simply registers, anything it can be. Operands can be anything. So this is the opcode, that what we are expecting from microprocessor. This is the opcode, and on which on whom we want to implement this, that signifies the operands. That signifies the operands. Now second one is the memory rule. Now second one is the memory rule. Second small point which I want to discuss is the memory rule. Suppose we have a data. Suppose we have a data like this. Suppose we have a data like this. So this we known as this we call higher byte. So this we call higher byte, and this we call as lower byte. This is called as lower byte. Now suppose I want to copy this data to this address, or suppose say we have HL register pair. We have HL register pair, and we want to copy this data here. We want to copy this data to the HL register pair. So always keep in mind that the lower byte always come towards the lower address location, always come towards the lower address location, and higher byte always come towards the higher address location, and higher byte always come to the higher address location. Lower byte, lower byte will always come at a lower address location. Higher byte will always come at a higher address location. So my content of HL pair will be 0203H. So now we will start with the most important topic of microprocessor, that is instruction set. That is instruction set. Today we will start most important topic of microprocessor, and that is instruction set. And in instruction set I have divided it into number of categories. So the first category which we are going to study is data transfer instructions. Is data transfer instructions. Is data transfer instructions. Is data transfer instructions. These are the list of data transfer instructions. These are the list of the data transfer instructions which we are going to study one by one, which we are going to study one by one, and that too in details, and that too in details. See, these lectures are going to be very interesting and very important also for your exam point of view, for your exam point of view. And I am going to take you in such a depth that you will just have a feel of how processing or execution of instruction is done by microprocessor. So after covering my lectures, you would not require to memorize these instructions. The feel which you will get, these all instructions will be on your tips, and by just looking at these instructions, you will be able to say that what functions they are performing, what all machine cycles are involved, how many T states are required, what is the length of instructions. This all questions will be easily solved by you without memorizing it. So be very attentive from now onwards, because we are going to enter into the last leg of our microprocessor, and that too a very important leg of our microprocessor. So let's see. The first important thing of data transfer instruction, the first important thing of data transfer instruction is that no flags are affected. 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 See, what will be my way of dealing with the data transfer instructions? What will be my way of dealing with the data transfer instruction? I am going to teach you this data transfer instruction in 4 categories. I am going to teach you this data transfer instruction in 4 categories. First one will be the function of the instruction. First one will be the function of instruction. First one will be function of instruction. Second one will be length of instruction. Second one will be length of instruction. See, based on length, the instructions in microprocessors are categorized as 1 byte instruction, 1 byte instruction, 2 byte instruction, 2-byte instruction and 3-byte instruction and 3-byte instruction. 3 byte is the maximum. 3 byte is the maximum length of any instructions in microprocessor. So you don't have to memorize that what all instructions falls under 1 byte or 2 byte or 3 byte. I am going to give you such feel of this of all the instructions that by just looking at the instruction you will say that what will be the length of this instruction. So you don't need to memorize instruction based on this length. There's no need. Just be with me and your instruction set will be very clear, and you will be able to solve any exam, any complex exam or any complex questions of gate or even conventional. Now if I come to third important thing, then I will tell you what all machine cycles are involved. What all machine cycles are involved. What all machine cycles are involved. See, if we talk about the machine cycles, then what are they? It is memory read, memory read, memory write, memory write, input output read, input output read, and input output write, and input output write. See, sometimes memory read is also known as opcode fetch. Sometimes memory read is also known as opcode fetch. Opcode fetch is also a kind of memory read function. Opcode fetch is also a kind of memory read function. But when microprocessor is fetching opcode from the memory, when microprocessor is fetching opcode from the memory, or when microprocessor is reading opcode from the memory, then it is known as memory read. Suppose we have this instruction. So I told you that this is a mnemonics which is understood by programmer, but it is not understood by microprocessor. So we have defined it a hexadecimal code. So we have defined it a hexadecimal code, and this hexadecimal code suppose the hexadecimal code is XXH. So this hexadecimal code is a kind of opcode. It is a kind of opcode or operation code for this instruction. Similarly, if we have another instruction, move immediate a comma 20h, here move immediate, it is the opcode, and we have assigned an hexadecimal code for it. So this hexadecimal code is known as the opcode. And when microprocessor reads this or fetches this from the memory, then it is known as the opcode fetch. So you can see that it is also a kind of memory read operation, but we are not reading data, we are reading opcode, so it is known as opcode fetch. While execution of any instruction, first machine cycle will always be opcode fetch. Because this only gives us the information, to microprocessor that what function it has to perform. See, this is only given information to microprocessor that it has to copy data from C to B. This is only given information to microprocessor that it has to transfer data 20H into accumulator. So first machine cycle is always opcode fetch. Now the fourth machine cycle. Okay, this is all about machine cycle. Now the fourth part which we will discuss is the calculation of T state. Calculation calculation of T states. Calculation of T states. This process we are going to look into in detail shortly, so don't worry. Calculation of T states. So see, if you are given any data transfer instruction, then these are the four type of questions which may be asked you either separately or jointly. They may ask you what is the function of instruction as a statement type question. They can ask you what will be the length of the instruction. They may ask you that how many machine cycles and what all machine cycles, how many and what all machine cycles are involved. And they may ask you to calculate the number of T states, and they may ask you to calculate the number of T states. So these are the four type of questions which comes for data transfer instruction. Now we are going to look each instruction, and for each instruction we are going to see all these details um, in a brief in a detailed manner. In a detailed manner you will just have a feel that how microprocessor is processing instruction, how microprocessor is processing instruction. Now coming to first instruction, and that is move rd comma rs. Move rd comma rs. Rd is destination register, rs is source register. So coming to our first part, that is what is the function or a description of this instruction. So its function is to move or copy or transfer the content of source register, to destination register, and after this copy or after this transfer of data from source to destination, the content of source register will remain unchanged. This is very important. Most of the time you think that cut and paste operation is going on. That is, after transferring this data, the data will not be available here. No, cut paste is not going on. Copy paste is going on. Copy paste is going on. The data which is transferred from here to there, that this data will be available with the source register. This data will be available with the source register. So this is my first part, that is the function part. Now we will come to our second part, that is what is the length of this instruction. What is the length of this instruction? So let me complete this diagram. This I have assumed microprocessor. This is my microprocessor. I have taken some part of microprocessor. Which is required for teaching you instruction set. This is my memory. This suppose I have considered as a data line. This I have considered as a data line. This I have considered as a address line. This I have considered as a address line. This I have considered as address line. This I have considered as address line. For address line, I am assuming that I am not going to teach you again this multiplexing and all. If I will tell you that address is moving from microprocessor to memory, it will be through this path, and it will be through this path. And if I tell you that data is flowing between microprocessor and memory, it will be through this path. It will be through this path. Now here we have some registers, like we have accumulator and flag register. Then we have a BC register. Then we have DE register. Then we have a HL register. And here is our program counter. And here is our program counter. And here is our program counter. Here we have instruction register. Here we have instruction register and a decoder. Here we have instruction register and a decoder. Here we have ALU. Here we have ALU. Here we have control unit. Here we have control unit. All these things are connected with each other. All these things are connected with each other. All these things are connected with each other. They are connected with each other. Now here we have our control signals. Here we have control signals like memory read, memory write, input output read, and input output write. Here also we are having a memory read. I am taking some small form because space constraint. Memory write, I hope you will understand it. Memory input output write and input output read. So here are our 4 control signals, and here we have 4 control signals. This is our memory. Let's suppose we are given an example. Let's suppose the starting address of memory is 3000H. Then here we will have 3001H, then 3002H, and so on, and so on, and so on. Now see how it works. How it works. So as a programmer, we first have to enter details of program into the memory. As a programmer, we first have to enter details of a program into the memory. We first has to enter details of program into the memory. So our program is, so let's take another page. Let our program is move B comma C. So I told you earlier also that this is mnemonics understood by programmer but not understood by microprocessor. Microprocessor only understand binary digits. So we have converted it into binary, and then we have converted it into a hexadecimal, and we have specified a unique code. We have defined a unique code for this instruction. Suppose it is XXH. We don't need to remember this codes. We don't need to remember this opcodes because it is not important for exam. It is not important for exam, and it is not important for programmers also. We have a list. We have a list where all the opcodes of each and every instructions are available. So programmer just refer those sheets and he enters the value into the memory. So this is our opcode. So this is our opcode. So this is our opcode in hexadecimal. So the programmer will first enter or feed this opcode into the memory. This opcode into the memory. Okay, fine. Now see, after feeding this opcode into the memory, now anything is left. Now anything is left to be fed into the memory. Is there any part of program which is left? which has to be feeded into the memory? No, we only had a instruction move b comma c. For this instruction we had a opcode, and we have fed that opcode into the memory. So see how much memory this instruction has taken. See how much memory this instruction has taken. See, I have told you earlier also said that these all are registers. These all are registers. Each register is made up of 8 flip-flop. That is, each register is of 1 byte. This is of 1 byte. This is also of 1 byte. This is also of 1 byte, and so on. So if I talk about the length of this instruction, length means how much memory space it has taken. So if I talk about the length of this instruction, then it is 1 byte instruction. Then it is 1 byte instruction. See, function I have told you. Function I have told you. Length I have briefed you. Length is 1 byte instruction. 1 byte instruction, because it has consumed only 1 byte memory. It has consumed only 1 byte memory. It has consumed only 1 byte memory. Okay, fine. Now coming to the machine cycles. Now next is to find out the machine cycles involved. Next is to find out machine cycle. Next is to find out machine cycle involved. So now see what will happen. Once the programmer has feeded his program into the memory. Once the programmer in a nutshell, if I tell you that how microprocessor works. So see, there's a programmer has a program. There's a programmer has a program which he has prepared using all these instructions: move b comma c, move immediate a comma some 8-bit data, sta lda. Using all these mnemonics or instructions, a programmer has prepared his data program. So the first thing the programmer has to do is to manually feed this instruction, this program prepared by him, into the memory. The programmer first of all feeds or inputs this program into the memory. After he has input all the program into the memory, then reset button is pressed. As soon as the reset button is pressed, program counter status becomes 0000h. Program counter status becomes 0000h. That is, now microprocessor knows that now it has to execute the program. Once the program counter becomes 0000h, then microprocessor knows that the programmer has feeded his program into the memory, and now the work of microprocessor start. So now the work of microprocessor start. So the first thing microprocessor will do is that it will originate this address 3000h. It will originate this address 3000h, and this address will come into the memory through address line. This address will come into the memory through this address line, and this memory location will be highlighted, and this memory location will be highlighted, and this memory location will be highlighted. What I told you, that first reset button will be pressed. Once reset button is pressed, status of program counter will become 0000h. Now microprocessor knows that it has to start its operation. So the first thing it sends is the initial address through address line, and it comes here, and this location gets highlighted. Now Before this, microprocessor was sitting idle. Before this, microprocessor was sitting idle. So microprocessor knows that if it is sitting idle, it means the by that time programmer is feeding his program into the memory. Programmer is feeding his program into the memory. So the first thing microprocessor has to do is to read memory. See, something is fed in memory. Something is fed in memory by programmer, but microprocessor doesn't know that what it is fed. So the first thing he has to do is that he has to read memory. It has to read memory. It has to read memory to find out that what functions microprocessor has to perform. What function microprocessor has to perform. So microprocessor will originate the control signal memory read. So microprocessor will originate a control signal memory read. So the first control signal which will be originated by microprocessor will always be memory read, because microprocessor wants to know and microprocessor has to know that what is demanded from microprocessor by the programmer. So this memory read will come here. This memory read will come here, and by this time, the content of program counter will change to 3001H. I told you that program counter always holds the address of next instruction to be executed. So now 3000H memory location is getting executed. Microprocessor is performing everything based on this memory location. So the program counter will shift one step further and it will come here, and its status will be 3001H, and it will come here. It will point here. So now memory read control has come to the memory. Now this opcode will be read. This opcode will be read, and it will be fetched, by the microprocessor, and through data lines it will come to the instruction register. Through data lines it will come to the instruction register. Now instruction register will forward it to decoder. Decoder will decode it, and microprocessor will now know that it has to move content of C, into B. It has to move content of C into B. Now see, both this B and C is inside microprocessor, so this function is executed, and or this instruction is executed. So what I told you that first, reset button pressed. As soon as reset button pressed, program counter comes to 0000H. Now the microprocessor sends the first memory address. It sends the first memory address towards the memory. This location gets highlighted. Now the first instruction of microprocessor will always now the first control signal of microprocessor will always be memory read, because microprocessor has to know that what all instruction is fed by the programmer. So microprocessor will generate memory read. Memory read will come here. By this time, program counter will shift to next memory location for the execution of next instruction. Now memory read will come here. This opcode will be fetched, or it will be read from memory, and through data lines it will come to instruction register. Instruction register will forward it to decoder. Decoder will decode it, and microprocessor will come to know that it has to transfer content of C to B. Now B and C both are inside microprocessor, so my function is performed. So my function or instruction is executed. So now if I talk about the machine cycle, then you can see that only one machine cycle was involved, that is opcode fetch. Only one machine cycle was involved, that is opcode fetch. Only one machine cycle was involved, that is opcode fetch. Only one machine cycle was involved, that is opcode fetch. So from all these details, now I think you must be getting the idea, you must be getting the feel that how processing is done with a microprocessor. How processing is done with a microprocessor. As we will move more forward, all these things will be more clear to you, and you will just enjoy it. You will just enjoy these sessions, because in this you are going to see that here you are going to visualize that how microprocessor works, works. So now the next thing which we have to find is the calculation of t state. This portion is very important. For conventional point of view. For objective, you will get questions on calculation of t states, but I will give you a trick. And you can just give the answer. But if this question is asked in conventional, then it will be asked for around 10 to 15 marks. And then there you have to follow my steps, and you have to solve or write this question in details. And this part is weak for many teachers. If you will refer lectures of many teachers who are teaching microprocessor, then you will see that most of them will skip this part. They will give you the idea of how to solve objective questions, but they will never give you the idea or briefing that how to solve question or conventional questions, and how exactly this t-state concept is working, But in this session with me, you are going to learn everything, and that too in details. Now, coming to calculation of t states. This is our clock pulse. This is our clock pulse. So this will be my T1. This will be my T1. This will be my T2. This will be my T3. This will be my T4. Suppose this is my T5 also, though T5 will not be required here, but still okay, we can define it. This is my T5. These are my clock pulses. Now suppose I draw one more drawing here, which we have learned earlier also. When we were doing memory mapping, then we saw this how address and data lines are working. That is how multiplexing of address and data lines were taking place. Suppose this is microprocessor. I told you that here we are having a higher order address line A15 to A8, and here there's a latch, and here we had lower order address line, and here we have a multiplexed line. Okay, then here we had control signals. Like input output read, input output write, or memory, or we can write it like this only. The three control signals which are available with us, and that is input output memory bar, read bar, and write bar. Then here I told you that we have a decoder. Here we had a decoder, and here we had a memory, and here we had memory. This will come here, and this were coming here, and then decoder used to then decoder used to highlight our memory. It used to highlight or activate. It used to highlight or activate our memory. This is our enable. This is our enable. So this diagram we have seen. This diagram we have seen, and then we also saw that how data used to come from this path, from data line. How data used to come from this line, the data line. So this part we have seen. This part we have seen. This is ALE. This is ALE. I will use this while explaining. I will use this while explaining T states. I will use this while explaining T states. So I have drawn a rough drawing here. So I have drawn a rough drawing here. So first let's start. So first let start with address line. That to higher order address line. That to higher order address line. I told you what was the sequence of steps. I told you programmer feeds the program into the memory, then reset button is pressed, and the program counter status changes to 0000H. Now microprocessor get the information that now it has to execute the program. So the first thing which microprocessor does is that it sends or it originates the address. It originates the first address, and we saw that our initially our address was 3000H. Our address, initial address was 3000H. See, okay. So we know that the higher byte will come at a higher order address line, and lower byte comes at lower order address line. So see, if I talk about the higher order address bus, if I talk about higher order address bus, if I talk about higher order address bus, then higher order address bus will be activated for 3 clock pulse. Higher order address bus will be activated for 3 clock pulse. It will be activated for 3 clock pulse because 3 clock pulse are required. Because 3 clock pulse are required by microprocessor if it is fetching, that is if it is reading or it is writing with memory. That is, we can say it in a simple word that 3 clock pulse are required by microprocessor for interacting with memory or coordinating with memory or interfacing with memory. That is 3 clock pulses are required. And once microprocessor has read or write data from and into memory, then it will take 3 clock pulses, and after that these address lines may be disabled. This address lines may be disabled. So I will see that after T3 what happens. I will tell you. So this is our higher order address line, and our higher byte is 30. So 30H will be saved here. 30H will be saved here, and it will remain here for 3 clock pulse. It will remain here for 3 clock pulse because I told you that 3 clock pulse are required by microprocessor for interfacing with memory. For interfacing with memory. For interfacing with memory. Fine. Now coming to lower order address bus. Now coming to lower order address bus. Now coming to lower order address bus. If I refer this drawing, then here also we saw that the higher order address bus will have a higher byte 30H. It will have 30H. It will have, and it will come at decoder. It will come at decoder. Now see, if I talk about the lower order address line, if I talk about the lower order address line, then lower order address line will act as an address line, for one clock pulse. It will act as a address line. Lower order, we know that lower order address line act as an address as well as a data line. So it will act as a address line for only one clock pulse. It will act as a address line for only one clock pulse. So our lower byte 00H will be copied here. 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 Now if I talk about ALE, now if I talk about ALE, if I, let's change the pen color. This is my A7 to A0. Now, if I talk about ALE, now if I will talk about ALE, address latch enable, See what will happen with this lower order address line for further clock pulse T states. I will see, I will brief you. Now coming to ALE, see, listen to it very carefully. If you listen 2-3 instructions, and if you can solve this T states, if you can solve calculation of this T states for 2-3 instructions, then rest will be easy. You will just complete it within 1 minute. Here I am taking time intentionally. Here I am intentionally taking time, and intentionally I am repeating things so that things becomes clearer to you. Becomes clearer to you. But once you will get accustomed with it, and then you will solve this type of questions within 2 to 3 minutes. The only time which you will take is the drawing all these things. Rest the concepts, it will be clear, it will be solved within 1 or 2 minutes. So but here I am intentionally taking time. I will intentionally take time for some more instructions also, but then after that, when things will be clear to you and you will become comfortable, then I will also push little fast. So now coming to ALE. See, ALE will be high. ALE will be high for one clock pulse. ALE will be high for one clock pulse. No, it will not be like this. ALE, ALE will be high. ALE will be high for one clock pulse. ALE will be high. ALE, ALE will be high for one clock pulse. ALE will be high for one clock pulse. See, let's see it from here. Let's remind it. Here I told you that higher byte of address will come into higher order address line. Lower byte of address will come here, this multiplexed line. And when ALE is 1, when ALE is 1, this latch will be enabled, and this lower order address will come here. Once this lower order address comes here, then ALE again becomes 0. And now this AD7 and AD0 will act like a data bus. It will act like a data bus, and it will not act like an address bus. And this 00H, that is lower byte of address, it will remain latched here. And it will remain connected with the decoder. So here ALE was high only for one clock pulse, and in that clock pulse my complete address line from A15 to A0 was acting like an address bus. So when ALE was high for one clock pulse, my complete address bus, that is from A15 to A0, was acting like an address line. And after that ALE has to become 0. Because I want these lines, to act like an data line. See, this all we have studied in details. This all we have studied in details in our previous lectures. But here, when we are combining T states, then you will get further clearance. You will get further, the concepts will get further clear to you. The concepts will get further clear to you once we are combining this memory mapping concept with a calculation of T state concept. Then concept will become much clear to you, and you will really conceptualize that how processing is done in the microprocessor. So what I told you, that ALE remains high for 1 clock pulse, because during this time our address bus will act like an address line, that is A15 to A0 will act like an address line. But after that I want my lower order address line to work as a data line, so ALE will be disabled, or it will become 0. It will become 0 and ALE will be disabled. So by this thing, ALE will be high for 1 clock pulse, and then it will be low for rest clock pulses. So after completion of these steps, we can see that now my memory, by now my memory location is highlighted or activated. Now my memory location is activated, because to activate memory location we require this enable pin to be active, and for this we require higher order address line and lower order address line, which has come to decoder, and now decoder will activate memory. Fine. Now coming to input output or memory operation. Now coming to input output and memory operation. So I told you that the first control signal which microprocessor originates is a memory read. It is memory read, because microprocessor has to know that what instructions programmer has fed into memory, and for that it has to first read the memory. So the first instruction will always be memory read. So it is active low. So we will have this active low. So once it has given, so once it has originated control signal memory, that it has to coordinate with the memory, then after reaching memory, it is found out that there is no requirement of interfacing with input output device. There is no requirement of interfacing with input output device. Everything will be between microprocessor and memory. So this pin will remain active low for the rest, because input output devices are not involved in this instruction. We only want to interface with memory, so this bit will remain low for rest clock pulses. See, now coming to whether we are performing read operation or we are performing write operation. We are performing read or write. So I told you that the first instruction which microprocessor will perform will be memory read, and in that opcode will be read and it will be brought back to the microprocessor. It will be read and brought back to the microprocessor. Now see, this reading writing part always take place at T2 and T3. This reading and writing part, always take place at clock pulse T2, T3. In T1 clock pulses, what we are doing is that we are highlighting memory location. Then microprocessor is sending memory read pulse. It is sending memory read pulse. But the actual reading and writing process, it will start from T2 to T3 plus. It will start from T2 to T3 pulse. Clock pulse. So read bar will be activated for T2 to T3. It will be activated for T2 to T3. Now we will write a memory read. Now we will write memory read. Memory read is a, you can say it is a kind of AND operation of input output memory bar and read bar. So it will also be activated for this. It will also be activated for this. For T2 to T3 clock pulse. It will also be activated for only T2 to T3 clock pulse. See, it takes a AND of this. It takes a AND of this. So it will be activated for T2 to T3. Here we have 0. Here we have 1. So it will be not high because it is a kind of active low. It is a kind of active low. It is a kind of active low. No, sorry. The memory read is a kind of NAND operation. Memory read is a kind of NAND operation. Memory read is a kind of NAND operation. It is a kind of NAND operation. So here we will get 1. But we want a 0. But we want a 0 because it is an active low input signal. Active low control signal. So what I told you, that in first clock pulse, the higher byte of address get latched with higher order address line, this higher order address line will remain active for T3 pulse because 3 clock pulse are required by microprocessor to read or write data from memory or input output device. So it will remain high for 3 clock pulse. Now, if we talk about the lower order address bus, if we talk about the lower order address bus, then the lower order address line, then in this ALE is high. ALE is high for first clock pulse. And during this time, this lower order address bus will act like an address line. So our lower byte 00 will be copied here. And then our ALE will be disabled. And this value will be latched with A7 to A0. And after that, it will act like a data line. Now I told you that the first instruction microprocessor has to perform is that it has to coordinate, it has to interface with memory, because it has to know that what instruction the programmer has feed it into the memory. So memory bit will be highlighted. So memory bit will be highlighted, and then after that I told you that the first machine cycle is always opcode fetch. It has to fetch the opcode of the instruction. So here the read bar will be active, and this read bar will be active for T2 to T3 because reading and writing process takes place at T2 to T3 clock pulses, not in T1 clock pulses. And then I told you that memory bar is a NAND combination of input output memory bar and read bar. It is a NAND combination. So here it will also be high. It will also be enabled. When both these are active low. Here it is active low. Here it is active high. So here you will find active high, and when it is 1, then it will be 0. But here it is active low. Active low, and now here it is active low. Here it is also active low. And we want active low. Then only this memory read will be activated. Now, once this is this control signal, reaches the memory, then the opcode fetch or opcode read will be done. And this opcode is latched with this lower order address line. this opcode will be latched with this lower order address line, because now it is acting like a data bus. But now, because now it is acting like a data bus, it is acting like a data bus. Once a microprocessor has originated memory read signal will come into the microprocessor, and now it will read the opcode, and this opcode will come into the data bus, because it will come into lower order address line, because now it is acting like a data bus. It is acting like a data bus. So this all process takes place for 3 clock pulses. It takes place for 3 clock pulses. If I want to add one more thing, that is a write bar. See, this all things must not be clear to you, so I am writing there here. This is a input output memory bar. This is input output memory bar. This is a read bar. This is read bar. This is memory read. This is memory read. Let me change the color also. So I can say that this is read bar, this is read bar, this is memory read, this is memory read, and this one is input output memory read. This one is input output memory read. Now here, if I want to add one more control signal, that is write bar. That is write bar. So in this instruction, we are not writing anything into the in this instruction we are not writing anything into the memory. So our write bar control signal will remain high forever. It will remain high forever. It will remain high forever. So this all things are taking place up to T3 clock pulse. So you will say that sir, everything has taken place, so why we require T4? Why we require T4? Why we require T4? So see, one clock pulse is required for execution of instruction by microprocessor. See, by 3 clock pulse, opcode fetch is brought into the memory, into the microprocessor. Opcode fetch is brought into the microprocessor, but now microprocessor has to decode it and execute the instruction. It has to decode it and execute this instruction, and this execution process takes 1 clock pulse. This execution process takes 1 clock pulse. This execution takes 1 clock pulse. This execution takes 1 clock pulse. This execution takes 1 clock pulse. So for 1 clock pulse, this all will be at a high impedance state. This all will be at a high impedance state, and this will be like this. So number of T state. So number of T state for execution of move B comma C. So number of T state. So number of T state. So number of T state. So number of T state for execution of move B comma C is 4T. Is 4T. Is 4T. So this is all about the calculation of T state, and this is how the microprocessor works. This is how microprocessor works along with clock, and here you will have detailed information. Here you will have detailed information of it. And if you will combine this diagram, if you will combine this diagram and you will combine this diagram, then now you have the clear picture of how microprocessor is working. Now you have the clear picture of how microprocessor is working. See, in this part, you may get a confusion. See, in this part, you may get a confusion, because when I was briefing you, then I skipped this part, or I was not able to explain you in a better way, because I was slightly distracted at that time. So let's see. let's see this part, and now it will be clear. I am rubbing this. I am this is my input output memory bar. This is my input output memory bar. This is my read bar. This is my memory read. This is my write bar. Okay. See, we have learned earlier also that using three control pins. We have learned earlier also that using three control pins, we originated four signals. We originated four signals by using this input output memory bar pin, by using read pin, and by using write pin. We originated four signals. What were those four signals? Those four signals were memory read, memory write, input output read, input output write. Now in this we are talking about memory read. Here we are talking about memory read. So this is our NAND gate. So this is my NAND gate. Input to this NAND gate will be this input output memory bar. Input output memory bar, and here we will have an inverter. Here we will have an inverter. Here also we will have an inverter. Here also we will have an inverter. Here we will have a read bar. Here we will have read bar, and in output we will have memory bar. In output we have memory bar. In output we want memory bar. That's why we are using inverter here, because we want a memory, because we want memory. If we want to deal with input output, then this inverter wouldn't have been here. This inverter wouldn't have been here. Now see, I told you that this memory bar, I told you that this memory read bar, will be activated for T2, T3, because for T2, T3, actual reading or fetching process takes place. And memory read bar, the inputs to memory read bar is this two. Input to memory read bar is this two. Now suppose if I am talking about T2, T3 state, if I am talking about this T2, T3, if I am talking about this T2, T3, then see, what is the status of input output memory bar for T2, T3? It is 0. So here we will get 0. Here we will get 0. This inverter will make it 1. Now what is the status of this read bar here? It is also 0. So this 0 will come here. This inverter will make it 1. 1, 1, 1, and output will be 0. That is my memory read bar. It is an active low control signal, so it will get activated. It will get activated. Now suppose we are talking about this. Now suppose we are talking about T1 clock. Now see what will be the status of all these three pins. Here the status of input output memory bar is 0. It always remains 0, because in this operation move a comma b, we are not interfacing with input output, we are interfacing with memory, so it will remain 0. Now I told you that read bar will be activated for only T2 and T3. Activated, it is a active low input. That's why when it is 0, then it is activated. When it is 1, it is disabled. So here it is 1. So see, if it is 0, then this 0 will come here. Inverter will make it 1. If it is 1 here, this 1 will come here. Inverter will make it 0. 1.0, 0. And at this output, we will get 1. That is, we will get one, that is memory read will be disabled. That is memory read will be disabled. That is memory read will be disabled. That's why memory read is enabled only for T2, T3, because it is a because it is a combination, of it is a NAND combination of input output memory bar and read bar. It is a NAND combination. It is a NAND combination of input output memory bar and read bar. So this was the process. If I talk about the read bar, if I talk about the write bar, so no writing process is taking place, so it will remain high. So this was all about the T states. Now coming to next instruction, that is move M comma R. Now coming to next instruction, that is move M comma R. You can say that it is just opposite of our previous instruction. You may say that it is just opposite of our previous instruction, which was move R comma M. Move R comma M. So now this instruction also we will look into 4 parts. So first part, if we come to the function of this instruction, then its function is move content of register to memory. Move content of registers to memory. So now see what it is saying. Suppose our instruction is move M comma B. B is a register. Suppose this is our microprocessor. This is our microprocessor. Content of register B is 10H. Content of register B is 10H. Content of register HL is 2005. Content of register HL is 2005. And this is my memory. Now this is my memory. Then meaning of this instruction. Meaning of this instruction is that we have to write this data, which is the content of register B, into this memory, into the memory. At which address or at which location? Here the address or location is the content of HL pair. Address or location is the content of HL pair. So in the previous lecture, in the previous instruction, what we did was, this content of HL pair was acting as a memory location from where we fetched data, and brought it into a particular register. Now what we are doing, what this instruction is doing, that the content of HL pair is still acting as a memory location, is still acting like a memory location. But now at this memory location we are writing data. From a register. Suppose in this case it is register B, so we are writing content of register B into the memory whose location or whose address is given by the content of HL pair. So if I compare this instruction with our previous instruction, or if I compare this instruction with move B comma M, then everything will remain same. But everything will remain same. Only thing is that here memory read operation was taking place. And here memory write operation will take place. So this is all about the function of this register. Now coming to the second part, that is the length of instruction. So here also it will be a 1 byte instruction. Here also it will be a 1 byte instruction. Its opcode is already defined. Suppose it is XXH. So XXH will come here. So now nothing is left. So it is a 1 byte instruction. it is a 1 byte instruction. Now coming to the third part, now coming to the third part, and that is number of machine cycle. So now coming to the third part, that is number of machine cycle. Number of machine cycle. So here opcode fetch will be like this only. Opcode fetch will be like this only. Only in place of memory read. Only in place of memory read we will have memory write. Only in place of memory read we will have memory write. We will have memory write. Now if we want to look into it in details, so if we want to look into it in details, that too in stepwise, then I will do modification in the previous instruction also, and I will explain you. So our step 1 was programmer will feed program or instruction in memory. Programmer will feed program or instruction in memory. Here our instruction was here our instruction was here our instruction was Here our instruction was this. Here our instruction is this. Here our instruction is this. So an opcode is already defined for it. Suppose it is XXH. That's why it is a 1 byte instruction. That's why it is a 1 byte instruction. That's why it is a that's why it is a 1 byte instruction. That's why it is a 1 byte instruction. Now step 2 is that reset button will be pressed, so my program counter will become 0000h. Now step 3 is microprocessor places starting address. Suppose here also our starting address is this 3000h on the address line. It will remain the same. Now step 4, microprocessor sends control signal memory read to fetch the opcode. It will be sent to fetch the opcode, and so the program counter will go one step ahead. So the program counter will go one step ahead to 3001h. Now step 5 is that opcode fetch operation will take place and opcode reaches microprocessor using data lines where it is decoded. It will also remain the same. Now step 6 is microprocessor will again send a address this into the address line. Here also if we assume that we have an HL register, whose content is 4000h. Now it will act like an address location. So microprocessor will again send address this into address line, and my program counter will become 4000h. Now here we will have a different control signal, because now we don't want to read data from memory, but we want to write data into memory. So I will say that here we will get memory write control signal is sent by the microprocessor. Memory write control signal will be sent by the microprocessor. So status of program counter will be 4001h. Now here also we will get a difference, that here 10h data is fed and brought into register B using data lines. Here 10h data, here I can delete it fully. Here also suppose we have a register B. Here also suppose we have a register B whose content is 10h. So now this 10h will be written into the memory. Whose address location is 400h, and this address location is same as the content of HL register pair. And here instead of memory read, we will send, not we will, microprocessor will send, not we will not send anything, but microprocessor will send memory write control signal here. Microprocessor will send memory write control signal here. Memory write control signal here. So now here we can write that 10H data, 10H data of register B, 10H data of register B will be written, will be written into memory, into memory, into memory, into memory whose address, whose address is 4000H. And this 4000H is nothing but it is the content of HL pair. This 4000H is nothing but it is the content of HL pair. It is the content of HL pair. It is the content of HL pair. So I think that it is clear to you that how memory write is coming here. Now coming to the number of T states. Now let's see how to find out the number of T states. Suppose it is given in objective question. Suppose you are given in objective question that what will be the number of T states for this instruction. So you know that what are our machine cycles? Our machine cycles are opcode fetch and memory write. So for opcode fetch we have 4T and for memory write we have 3T. So it will also be 7T. Number of T states will be 7. But here we will analyze it. We will study it in details that how the processing take place. So let see this part also. And this also I will compare it with the previous one. So I will complete it first. Now coming to calculation of T states. Now coming to calculation of T states. So I will refer the previous instruction and here only I will do some minor modification. So this is our instruction. Starting address is 3000H, move M comma R. So here I told you that this is our A15 to A8, that is higher order address line. It will be high for 3T states. It will be high for 3T states, and during this 3T states, it will have the higher byte address. It will have higher byte address. Now for remaining 1T state, suppose I am just talking about opcode fetch part, then I will discuss the memory write part. So if I am talking about opcode fetch part, so for 3T states it will be high and it will have a higher byte of address, and for remaining 1T state it will be at high impedance because during this T state microprocessor is decoding instruction. So there is no requirement of any address line or there is no requirement of any data line also. Now coming to the lower order address bus, it will act like an lower order address bus for 1T state for which ALE is high, So at this time it will have a lower byte of address. Now coming to a control signal, input output memory bar. So we are in this instruction also we are dealing with memory. So this pulse will remain low because it is an active low control signal. Now coming to read bar. So I told you that read bar will be active. It is also an active low control signal. So it will be active for T2 and T3. Now coming to memory read control signal. So it will also be active for T2 and T3. For T2, T3, we can see that both read bar and memory read are active. Both are active low control signal. And no, coming to this, first we will take this here for T2 and T3. Here for T2 and T3, we can see that input output memory bar control signal and read bar control signal both are active low. Both are active low. So for memory read, which is a NAND combination of both this, we will get it as active low for T2 and T3. So during this period, the opcode of memory, opcode of this instruction will be copied into lower order address bus, because at this time it is acting like an data bus, and it will be brought back into the microprocessor. And here also for remaining 1T state, it is in high impedance, because at this time microprocessor is decoding this instruction, so there is no requirement of any address or data line. Okay, fine. Now coming to the second part, my opcode fetch was finished here. So now coming to the second part, that is memory write. So here also for T3 state, our higher order address bus will be enabled, and our higher byte, and this case the content of HL was content of HL was 4000 H. Now this will act like a memory location, so its higher byte will come here. Now coming to lower order address bus, for 1T state it will act like a address bus, so lower byte will come here. ALE will be high for 1T state. Here again we are dealing with memory, so there will be no change here. But here, this read bar, in this duration, we are not reading from memory, but we want to write from memory. So this control signal, read bar control signal, will be active high. It will be in high state. It will be disabled. That is, this will be disabled. Now here we are not writing anything into memory. But here we are not reading anything from memory. But here we are writing into memory. But here we want to write into memory. So here we will come later. First we will discuss this control signal, write control signal. So in this case, my write control signal will be at active low for 2T states, that is T2 and that is T6 and T7. Because during these two T states, reading and writing operation takes place. So for T6 and T7, my write bar control signal will be low, and my input output memory bar control signal will be low. Now this input output memory bar and write bar will be taken as a NAND combination. So we will get memory write control signal low for T6 and T7. So during this stage, our data 10H, which was stored in our register, our data 10H, which was stored in register, will be written into the memory, whose address location is 4000H, and this 4000H is nothing but content of HL pair. So here also we can see that total T states required is 7T. So these were our two very important instructions, where students generally have lot of confusion, and I hope that I have discussed both these instructions in detail and you have understood it. So This was all about these two instructions. Now we will move into our next part. Now coming to another instruction. And that is move r comma m. Now coming to another instruction, and that is move r comma m. So this instruction also we will look into four parts. So this instruction also we will look into four parts. First will be the function. First one will be the function of this instruction. Function of this instruction. Second one will be the length of this instruction. Second one will be length of this instruction. Length of instruction. Third one will be number of machine cycle. Third one will be number of machine cycle. Number of machine cycle. Number of machine cycle. And fourth one will be number of T states. 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 So coming to the function of this instruction, move r comma m, it is move content of memory to register. Move content of memory to register. So this instruction we have seen earlier also. This instruction we have seen earlier also. This instruction we have seen earlier also, where I told you that this M is a memory register. It is a memory register which points HL register pair. It is memory register. It is memory register which points HL register pair, which points HL register pair, which points HL register pair, which points HL register pair. Now suppose we have a microprocessor. Now suppose we have a microprocessor and we have a HL register pair, and we have a HL register pair. We have a HL register pair, and the content of HL register pair is suppose 2005. Now we have a memory. Now we have a memory. Suppose memory is having a memory location. Suppose memory is having a memory location 2005H, and the content of this memory location is 10H. Content of this memory location is 10H. Then what is the meaning of this instruction? What is the meaning of this instruction? Meaning of this instruction is that we have to fetch data from memory. We have to fetch data from a memory whose location is the content of HL register pair. Whose location or address is the content of HL register pair. The meaning of this instruction is that we have to copy or read or fetch data from memory whose location or address is the content of HL register pair, and after reading the data, this data, we have to copy it into register R. We have to copy it into register R. We have to copy it into register R. So here the content of HL register pair, is acting as a address, That's why HL register pair is also known as default memory pointer. That's why HL register pair, HL register pair, HL register pair, HL register pair is also known as default memory pointer, is also known as default memory pointer, is also known as a default memory pointer. So I hope that the function is clear. So I hope function of this instruction is clear. Function of this instruction is clear. So let me just completely fill all this. This is my microprocessor. This is my microprocessor. This is my memory. This is my data lines bidirectional. This is my address line unidirectional. This is instruction register and decoder. This is ALU. This is ALU. This is CU. Here we have accumulator, flag register, BC register, PE register, HL register, program counter. And here we are having memory read control signal, memory write control signal, input output read control signal, input output write control signal. Here also we are having memory read control signal, memory write control signal, input read control signal, and input write control signal, and input write control signal, input write control signal. Suppose we have an example. Suppose we have an example of this instruction. Suppose we have an example of this instruction where the starting memory address is 3000H. Starting memory address is 3000H, and the instruction which is given is move B, M. Instruction which is given is move B, M. So in the last instruction, I gave you the full details of the processing part. I gave you the full details of processing part, so that how we can find the length of the instructions, that how we can find the length of the instructions, and how we can find the number of machine cycles. And then I discussed that how we can find the number of T states. And then we discussed that how we can find the number of T states. That was descriptive part. That was a descriptive discussion. That was descriptive discussion. In this instruction, in this example, I am going to discuss stepwise. I am going to discuss the processing and the execution part. I am going to discuss this processing and execution part stepwise, because sometimes stepwise becomes easier to understand and memorize. So what will be my first step? So what will be my first step? First step is that programmer has to feed program. Programmer will feed program. Programmer will feed program in memory. Programmer will feed program in memory. So what is the instruction? Here we can say program or instruction. Here we are having only one instruction. Group of instruction becomes a program, but here we are having only one instruction. So the instruction is move B, M. Move B, M. This is mnemonics. This is mnemonics. We have a hexadecimal predefined opcode for it. We have a hexadecimal predefined opcode for it. Suppose it is XXH. So programmer will feed XXH. Programmer will feed XXH in the memory. It will feed XXH in the memory. Now see, if anything else is required to be fed into the memory, is anything else is required to be fed in the memory? No, nothing is required to be fed in the memory. So it is also 1 byte instruction. It is also 1 byte instruction because it is taking 1 byte space in the memory. Because it is taking 1 byte step, 1 byte space in the memory. Now coming to step 2. Now coming to step 2. Now programmer will press. Now programmer will press reset button. After feeding the program or instruction, programmer will press reset button. Once reset button is pressed, the program counter status will be 0000H. Once reset button is pressed, once reset button is pressed, the status of program counter will become 0000H. It will become 0000H. Now what will be my step 3? Now microprocessor gets the information that it has to start its execution. Microprocessor gets the information that it has to start its execution. So the first thing microprocessor will do is that it will originate this starting address. It will originate this starting address, and it will place this address into the address line. It will place this address into the address line. So we can write microprocessor places starting address, in this case it is in this case it is 3000H. In this case it is 3000H on address line, or address bus, fine. Now through this address line, 3000H will come to the memory, and this memory location, gets highlighted, and this memory location gets highlighted. Now as this is the first operation of microprocessor, now as this is the first operation of microprocessor, now as this is the first operation of microprocessor, so its next step will be, as this is the first operation of microprocessor, so microprocessor will send a control signal memory read. So microprocessor will send a control signal memory read. Here we can write microprocessor sends control signal memory read, because till now microprocessor doesn't know that what it has to perform. So to know the instruction, it has to send the first control signal as memory read, so that it can read the opcode, and then after it gets an idea that what exactly it has to perform. So microprocessor will send control signal memory read, and this memory read will come into the memory. By now, the status of program counter will be one step forward. It will be one step forward. So its status will be 3001H. So its status will be 3001H. Fine. Now, now, as memory read control signal has come to memory, so the opcode will be fetched. So opcode will be fetched, or it will be read, and through data line, it will come into the instruction register. Through data line it will come into the instruction register, and there it will be decoded. And now the microprocessor knows that what exactly it has to do, all these are connected, with each other. So if we talk about the next step, step 5, opcode fetch operation. Opcode fetch operation will take place, and opcode reaches microprocessor using data lines where it is decoded, where it is decoded, where it is decoded, where it is decoded. So now after it is decoded, microprocessor gets the information that it has to again fetch a data from memory. It has to again fetch a data from memory. Let's suppose the content of HL pair is 4000H. Suppose content of HL pair is 4000H, and here somewhere we are having address location 4000H, and suppose the data is 10H. So once the instruction is decoded, then microprocessor gets the information that it has to fetch a data, from memory whose address is content of HL register, whose address is content of HL register, whose address is content of HL register. So what will be the next step? If I talk about step 6, microprocessor will again send address, 4000H into address line, into address line, So the content of HL register, this content of HL register will be placed in the address line. It will be placed in the address line, and this memory location, will get highlighted, and this memory location will get highlighted, microprocessor knows that it has to fetch data from memory. Microprocessor knows that it has to fetch data. So microprocessor sends signal address, which is the content of HL pair 4000H, into the address line, and it will come into the memory, and it will highlight this memory location. At this instant, what will be the content of program counter? Content of program counter will be 4000H. It will be 4000H. Now, what will be the next step? The next step, microprocessor now knows that it has to again fetch data from memory. So it will again send memory read control signal. So step 7. memory read control signal is sent by microprocessor, and this control signal will reach the memory. Now at this instant, what will be the content of program counter? It will be one step further. That is 4001H. That is 4001H. Now the memory fetch or memory read operation will take place, and this data through data bus will come into the microprocessor, and it will come inside register B. So what will be our next step? Next step is step 8. 10H data is fed. 10H data is fed and brought and brought into register B using data lines using data lines. So if we talk about the number of machine cycles, then here you can see that there are two machine cycles. One is the opcode fetch and memory read. Here we have two machine cycle. One is the opcode fetch and another one is the memory read. Now see, if we again look into it, then see what is our first step. First, programmer will feed the program or instruction into memory. Then reset button will be pressed. Then microprocessor places starting address 3000H on the address line. Then microprocessor has to perform opcode fetch. First operation is always opcode fetch. So microprocessor will send control signal memory read into the memory, and then opcode fetch operation will take place, and opcode will come into the microprocessor through data bus, where it will be decoded. After it is decoded, microprocessor gets the information that it has to again perform memory read operation, and data has to be fetched from memory location, which is the content of HL pair. So again, now again the content of HL pair 4000H will be placed into the address line. Now this address location will get highlighted in the memory. Now again read operation has to be performed. So memory read control signal will be sent by microprocessor, and now 10H data is read, and it is brought back into the microprocessor. So it is a 1 byte instruction, and it has two machine cycles. I hope this is clear. Now let's see the calculation of T states. Now coming to calculation of T states. So this is T1. This is T1. This is T2. This is T3. These are our 7 T states. So we will start with higher order address bus, that is A15 to A8. So higher order address bus. Higher order address bus will be high for 3 T states. It will be high for 3 T states. Higher order address bus will be high for 3 T states. because three clock or three T states are required by microprocessor for reading or writing data from memory or into memory. And same is for I can add input output device also. So though I have not covered input output instructions yet, but I can give you a general statement that three clock pulses are required by microprocessor for interfacing with the memory as well as input output device, for memory as well as input output device. So you will say that sir, if it's so, then why four T states are used for opcode fetch? Why four T states are used for opcode fetch? Then I will say you that one T state is used for decoding opcode. One T state is used for decoding opcode, and that decoding takes place only once in a instruction. That decoding takes place only once for one instruction. So we have one extra T state, and for that extra T state we don't require a address bus to be enabled, or we don't require data bus to be enabled, because everything has now switched to microprocessor. All the data and everything which is required for processing has now shifted to microprocessor, and now microprocessor is decoding it. And for that one T clock pulse is required, and all other address and data bus can be disabled, because now no movement of any data or memory is taking place. So let it be. So if I talk about A15 to A8, this is a higher order address bus. It will be enabled for 3 clock pulse, and the higher byte the higher byte of address will be placed here. The higher byte of address will be placed here. Fine. Now coming to lower order address bus. So first of all, it will be high for 1 T state. It will be high for 1 T state. During this time ALE is high. So it is acting like a address bus, and the lower byte of address will be stored here will be stored here. And after that ALE will be disabled. So after that, this lower order address bus will act like a data bus. So now if I talk about ALE, then ALE will be high. For one clock pulse. ALE will be high for one clock pulse, and during this clock pulse, this lower order address bus will act like a address bus, and after that, when ALE is disabled, it can act like a data bus. Now if I talk about input output and memory bar, this control input output and memory bar control pin, then for first step, always microprocessor has to interface with memory. So it will be active low. Because for the first function which microprocessor performs is output fetch, and for that we require memory read control bit. Now if I talk about read bar, if I talk about read bar, then I told you that reading process takes place in clock pulse T2 and T3. Reading process will take place in the clock pulse T2 and T3. So it will be active low for T2 and T3. Now if we talk about memory read, talk about memory read. Now if we talk about memory read, so what is memory read? It is NAND operation of this two. It is NAND operation of this two. It is NAND operation of this two. So it will also be active low only when this both are active low. That is for T2 and T3. So it will be active low when both these are active low. That is for T2 and T3. And if we talk about the right bar control signal, then it will always be high. It will always be high. No, I will not say it will always be, yes, it will always be high, because here we are not performing any memory write operation. Here we are not performing any memory write operation. Uh, um, Suppose I'm not, let's say, don't consider the second part, just focus on this part. So for the first part, that is when opcode fetch is going on, when opcode fetch is going on, then there is no requirement of any write control signal, because here memory read is taking place. So this is all about our clock pulse T1, T2, T3. T1, T2, T3. After T1, T2, T3, you can see that all required things which microprocessor wanted from the memory has come inside the microprocessor. Now microprocessor doesn't require to interface with memory. So this address line will be disabled for the clock pulse T4. It will be disabled. Let me add one more thing. Here, that when this memory read operation control bit is when this memory read control signal has reached memory, then what will happen? The opcode fetch operation will take place. And the opcode of instruction will be stored in data lines, and it will come inside the microprocessor. So now after this, I was saying that after T3 clock pulse, my main the main motive of microprocessor was opcode fetch. Now this opcode fetch has come inside microprocessor, so now microprocessor doesn't need to interface with memory. So this address line can be disabled. This data lines can be disabled. They are at high impedance state. ALE will be low. This input output memory bar, it will be active low. Read bar, it will be active high. Memory read, it will be active high. And write bar, it will be active high. So this one T state is required by microprocessor for decoding this opcode. It is required by microprocessor for decoding this opcode, so that it will understand that what operation it has to perform. And during this, there is no interfacing with the memory. And if we will discuss input output, then that also during this time there will be no requirement of interfacing with input output devices. So now for T4, my opcode fetch is complete. Now up to T4, my opcode fetch is complete. Now if we talk about the second machine cycle, that is my memory read. If we talk about the second machine cycle, that is memory read. So see what will happen here. Here again, higher order address line, it will be enabled for 3 clock pulse. It will be enabled for 3 clock pulse. And here we have seen, no, not here. Here we have seen that now that all processing will be at address location 4000H. All processing will be at address location 4000H. Fine. All processing will be at address location 4000H. So now 4000H is the address location. So in the higher order address line, this 40H will come. At higher order address line, this 40H will come. Now in lower order address line, for one clock pulse, for T5, it will have 00H, it will have 00H. Now again ALE will be high for one clock pulse. Now again ALE will be high for one clock pulse. Now if we talk about the input output memory bar, so it will be active low only, because interfacing with memory is taking place, If we talk about the read bar, if we talk about the read bar, then it will be active low for T6 and T7. It will be active low. It will be active low for T6 and T7. It will be active low for T6 and T7. If we talk about the memory bar, then it will be active low for T6 and T7, because it is a kind of NAND operation between these two. If we talk about the write bar, so it will always be active high, because we are writing into from the microprocessor. We are nothing writing into the microprocessor. After this memory read, what will happen? The content 10H, which was at memory location this, the content or data 10H, which was at memory location this, uh, it will be it will be saved here. It will be saved into the data bus. It will be brought back into the microprocessor, and it will be copied into register B. It will be copied into the register B. It will be copied into the register B. It will be copied into register B. So now this process, so the first opcode fetch required 4 T states, but this machine cycle memory read required 3 T states. So you will say that again, sir, 1 T state is required for decoding and all. No, decoding is done only for the opcode. Once opcode is decoded, microprocessor know that what all rest thing it has to do. So there is no requirement of another clock pulse, because here we are not sending any opcodes. In this process we are not sending, here we were sending the opcode, but here we are not sending any opcode. We are just sending the data, and this data has to be saved into the register B, which is already in the microprocessor. So if we talk about the number of T states here 7 T states are required. 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 So now if I want to give you a general statement of T states, so for opcode fetch, 4 T states are required. 4 T states are required. You know, I have divided it into 3T and 1T. In 3T, everything will come inside the microprocessor, and for the remaining 1T, decoding will take place. Decoding will take place inside the microprocessor. Now, if we talk about memory read, the number of T states required will be 3T. If we talk about memory write, number of T states required will be 3T. If we talk about input output read, number of T states required will be 3T. If we talk about input output write, then number of T states required will be 3T. So you can see that except opcode fetch, which is requiring 4T states, All other operations require only 3 T states. All other operations requires only 3 T states. So now if this question is given you in objective exam, if this question is given you in objective exam, so now if this question is given you in objective question exam, then you know there's no need of solving all this. There's no need of solving all this. Just by knowing the machine cycles, just by knowing the machine cycles, that what all machine cycles are required for execution of this instruction, you can simply conclude the number of T states required. That is, in this instruction, 2 machine cycles are required. That is opcode fetch and memory read. For opcode fetch, the 4T are required, and for memory read, 3T are required. So total 7T is required. 7T is required. And if you will refer lectures of other teachers, then what they do is that they give you this details only. They give you this details only, that you just memorize it, that in this 40 and rest 3T are required, and then you can solve all the objective question. But they will not teach you the base behind it, the logic behind it, the processing behind it. And without this processing, you will not get the feel of the subject. And if this question is asked in conventional for 15-20 marks, then if you will just write 70 state, then they will give you either 1 marks, or they can give you either 1.5 marks only out of 15 marks. So this complete details is required to get a feel of the subject. Rest, if we talk about the shortcut, then you just remember this, that for opcode fetch 4T is required, and for rest 3T is required, and you can easily solve the question, provided you know that what all machine cycles are required, what all machine cycles are required for execution of this instruction. Now, coming to next instruction, that is MVIR, 8-bit data. MVIR, 8-bit data. MVI is move immediate. Move immediate. For all the instructions, which have I, like here MVI means move immediate. MVI means move immediate. Similarly, we will see our next instruction, which will be LXI, which will be LXI. That is load immediate. Immediate. I for immediate. I for immediate. For such instructions, opcode is always data and not address. Opcode is always data and not address. In this case, with MVI, we have 8-bit. We have a 8-bit only. So from 8-bit, we will know that address cannot be 8-bit. So obviously, this is going to be data. This is going to be data. But for LXI, register pair, we will see this instruction, but still I am giving you some information. LXI register pair 16-bit. Here we will have 16-bit. Here we will have 16-bit. So student generally gets confused that whether this 16-bit is going to be address or this 16-bit is going to be data. So always remember, for the all the instructions which has I, that is immediate, load immediate, move immediate, the operand is always data. The operand is always data. Operand is always data. Operand is always data. Operand is always data. I hope this is clear. So now, if we talk about this instruction, it is move immediate 8-bit data in register. Move immediate 8-bit data in register. Now, again, we will look into it in 4 parts. Again, we will look into it in four parts. That is function. That is function. Second one will be length. Second one will be length. Third one will be machine cycle. Third one will be machine cycle. Fourth one will be T states. From now, you can see that how you can easily find out all these things. How you can easily find out all these things from our previous discussion. So if we talk about function, if we talk about function, suppose we have instruction like this: move immediate b comma 10h, move immediate b comma 10h. So here we know that it is move immediate, that we have to move this data, into register b. And where is our data, 10h? It is in memory. Then obviously from here you can conclude that first thing we have to do is that we have to fetch the opcode. We have to first fetch the opcode, and then we have to fetch the data from the memory, and then we have to fetch the data from memory. Suppose this is our microprocessor. Here we are having register B. Here we are having register B, and here we have memory. And here there is data 10h. So we have to move this data 10h from memory into microprocessor, into register B. So from this instruction, you should get a concept of this, that what exactly is going to happen. And now if you has the idea of what exactly is going to happen, then rest all things just becomes a formality. Rest all things of finding the length, finding the machine cycles, finding the t states, all are just formality. It will be you can get all these things within seconds. Just you should know what is the meaning, or what is the description, or what is the function of the instruction. So okay, so function is clear to us. Now talking about the length. Suppose this is our instruction. So if let me complete this. BC, DE, HL, PC, instruction register, and decoder, ALU, control unit, and all are connected, with each other. Starting address is 3000h. So what is our instruction? Our instruction is move C, 88h. We have to find the length of this instruction. So if we talk about our step 1, so now first the programmer has to feed this instruction. The programmer has to first feed this instruction into memory. So first programmer will feed this opcode. Into the memory. So suppose the opcode is opcode is XXH. It is 1 byte. It will take 1 byte. It will take 1 byte. So here we will have XXH. Okay, fine. Now, programmer, programmer has to feed this data into the memory. Now programmer has to feed this data into the memory. So where this data will be fed? It will be fed in the next address location. It will be fed in the next address location. In the next address location. So what will be the length of this instruction? Length of this instruction will be 2 byte. Length of this instruction will be 2 byte. I hope it is clear. See here, first we see what we see. First we see the opcode. The programmer first has to feed the opcode into the memory, and then programmer has to feed data into the memory, and by doing so, uh, 2 byte memory location is used. 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 Okay, fine. Now coming to the machine cycle. Now coming to the machine cycle. So here only we discussed that the meaning of this instruction is that we have to fetch this data from memory into microprocessor. So obviously the first thing will be our opcode fetch. First thing will be our opcode fetch, and first thing will be our opcode fetch, and second thing will be memory read. 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 So here we have already got the overview. So here we have already got the overview. Now if we will write it stepwise, then what will happen? Step 2, after entering all the data, reset button will be pressed. After entering all the data into the memory, reset button will be pressed. Reset button will be pressed. So status of program counter will be 0000H. Okay, fine. Now the first thing which microprocessor will do is that it will send starting address. It will send a starting address onto the address bus, because microprocessor wants to know that what instruction is fed by the programmer. So what will come here? Our starting address is this 3000H. It will come in address bus. Now from now I will write it in short form, because we have already discussed all this thing. You are already comfortable with all this thing. So I will write these steps and all for 1 and 2 instructions more, and then I am going to just verbally brief you. So 3000H in address bus, in address bus, in address bus. Here 3000H, 3000H in address bus, in address bus. Now this address location will be highlighted. Now this address location will be highlighted. Now microprocessor wants to fetch this opcode. Microprocessor wants to fetch this opcode. So microprocessor will send memory read control signal. Microprocessor will send memory read control signal. Memory read control signal, memory read control signal, and then this opcode will be fetched and it will be brought back to the instruction register through data bus. This all we have seen. So here we can write for step 4, memory read control signal will be given by microprocessor, and now the status of program counter, it will jump to the next address location. it will jump to the next address location. It will jump to the next address location. So now if I talk about the step 5, now step 5, now the opcode will be fetched. Opcode is fetched. Opcode is fetched, and it will be brought back to microprocessor, and it will be brought back to microprocessor using data lines, using data lines, using data lines, using data lines. And now here it will come to instruction register, and it will be decoded, 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 and it will be decoded. Now after decoding it, microprocessor knows that it has to again go into the memory. It has to again go into the memory. It has to again go into the memory to fetch data, and bring it back to the microprocessor into register C. Bring it back to the microprocessor into register C. This microprocessor gets the information. This microprocessor gets the information. So again the address location, address location 3001H will be originated from the microprocessor, and it will be placed on the address line. It will be placed on the address line. It will be placed on the address line. So now this 3001H address location will get highlighted. It will get highlighted. It will get highlighted. Now our step 7, after highlighting this memory location, again memory read control signal will be originated. Again memory read control signal will be originated, because we want to fetch this data, Now during this time, our status of program counter will be, it will jump to our next memory location, that is 3002H. Now step 8, the data 88H will be read, or it will be fetched, and it will be brought to the microprocessor using data line into register C, into register C, into register C. So this was into register C. Here first opcode will come, and then here data lines will come. Here address location 3000H, and then we will have address location this here. Memory read, it will come 2 times. Memory read, it will come 2 times. So this was all the working of microprocessor related to this instruction. So we have two machine code. One is the opcode fetch, one is the opcode fetch, and second one is memory read. Second one is memory read. Second one is memory read. So fine. Now coming to the number of T states. So now coming to the number of T states. If you are asked in the objective question, so now you can write it directly. For opcode fetch, you will have 4 T states. For memory read, we will have 3 T states. So total we will have 7 T states. 7 T states. But we will look into it in details. For understanding point of view and for conventional point of view. I will take it in details for 2 to 3 instructions more, and then we will try to skip it. Because by that time, more or less, we will have a very good understanding and idea of how we calculate the T states. Now, coming to calculation of T states. So here we have taken 7 T states: T1, T2, T3, T4, T5, T6, T7. Now see, here again, we will first talk about the higher order. Here again, we will first talk about the higher order address line. Higher order address line. Higher order address line. So as I told you earlier, higher order address line it will be high for 3t states. It will be high for 3t states, and during this 3t states, it will have a higher byte of address. It will contain higher byte of address. It will contain higher byte of address. Fine. Now coming to lower order address bus. Now coming to lower order address bus. So as I told you earlier also, it will be high. It will be high for 1t states. That is, for 1t state, it will act like an address bus. It will act like an address bus, and during this time it will have a lower byte of address. It will have lower byte of address. Now coming to ALE. Now coming to ALE. So ALE will also be high. So ALE will also be high for 1t state. So ALE will also be high for 1t state, and during this t state, lower order address bus acts as a address line, and after that it will act like a data line. So ALE will be high for 1t state. Now coming to input, output, and memory bar. So here also we are dealing with memory only. Here also we are dealing with memory only, and it is an active low signal. So it will be active low from starting. From starting only. It will be active low from starting only. Now if we talk about read bar. Now if we talk about the read bar control signal, if we will talk about the read bar control signal, then I told you that it will be enabled for t states t2 and t3, because for t2 and t3 read write process or operation take place. Read write operations takes place. So it will be enabled for T2 and T3. It is also a active low control signal. It is also a active low control signal. Now if we come to memory read control signal, if we will come to memory read control signal, then it is a NAND combination of both these two. It is a NAND combination of both these two. So it will also be enabled for T2 and T3 only. It will also be enabled for T2 and T3 only. Now if we talk about write bar control signal, if we will talk about write bar control signal, so here we are not writing anything into memory. Here we are not writing anything into memory. So it will be high. So it will be high always. That is, it will be disabled always. That is, it will be disabled always. That is, it will be disabled always. So here, after doing memory, after this memory read control signal is active, after this memory read control signal is active, my opcode will be fetched into lower order address line, which is now acting like a data line, which is now acting like a data line. Okay, fine. Now for this, all is for three T states. For remaining one T state, address line will be at high impedance, data line will be at high impedance, because during this period there is no requirement of any address line or data line, because microprocessor is using this T states for decoding instruction, for decoding instruction, for decoding instruction, for decoding instruction. So this was all about our first machine cycle, that is opcode fetch, that is opcode fetch. Now coming to our second machine cycle, that is memory read, that is memory read. Here also, if we talk about the higher order address line, so it will be again high for T3 states, for 3T states. And what it will have? It will have a higher byte of our next address line, where data 88H is stored, where data 88H is stored. So 30 will come here, 30 will come here. Now we will get for, if we talk about the lower order address line, So it will be high for one T state when it is acting like a address line, and it will have lower byte of address line, and it will have lower byte of address. It will have lower byte of address. Now here again ALE will be high for one T state. ALE will be high for one T state when this lower order address line, when this lower order, when this lower order address line will act like a data line, and after that it will act like a address line, and after that it will act like a data line. Now again coming to input output and memory bar, here also we are dealing with the memory, so it will be enabled, it will be enabled. Now coming to read bar, again we have to read it from memory, again we have to read it from memory, so it will be enabled for T6 and T7. It will be enabled for T6 and T7. Now coming to memory read. Now coming to memory read, it is a NAND combination of both these two. NAND combination of both these two. So it will be enabled for T6 and T7. It will be enabled for T6 and T7. Now coming to write bar, we are not writing anything into memory, so it will be disabled. So this will be disabled. So here also and here after completing this memory read, after completing this memory read, our data 88H, our data 88H will get latched. It will get latched with the lower order address line, which is now acting like a data 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 line. So this was all about our description of T states. Here also we can see that total T states required is 7T. Total T states required, total T states required is 7T. So this was all about our instruction move immediate C comma 88H. Here I told you that I immediate means it is going to be a data. It is going to be a data. Here it is a 8-bit, so there is no confusion. It will be data only because address is not of 8-bit. But next we will see about load immediate LXI. There you will get confusion that what is this what is this 16-bit what is this 16-bit? It is either address or data, so it is always data. I immediate data, I immediate data. So this was all about our this instruction. Now coming to our next instruction, that is LXI register pair 16-bit data. LXI register pair 16-bit data. What is its meaning? It is load immediate 16-bit value into register pair. Load immediate 16-bit value into register pair. As I discussed in last instruction also, that is I for immediate, that is it is going to be a data. Don't confuse this 16-bit thing with address. It is going to be a data when it is I for immediate. When it is I for immediate. So again, let discuss it in by categorizing it into 4 parts. First one is the function. First one is the function. Then second one is the length. Second one is the length. Third one is machine cycle. And fourth one is T state. Fourth one is T state. Fourth one is T state. So let's suppose we have instruction like this, load immediate. Take it something like this, D into 16-bit data, that is 2020H. 2020H. LXI is always related with register pair. It is always register. So it is always LXI means it has to be a register pair. It has to be a register pair because our data is 16-bit, and 16-bit data will never come into 8-bit register. It can never come into 8-bit register. So even if in the exam it is written only D, even if in the exam it is written only LXI D, you should know that it is not a D. It is talking about a DE register pair. It is talking about DE register pair, because if you want to move this data into register, then it has to be only register pair, because register pair is of 16-bit and individual registers are only of 8-bit. So now see what this instruction means. What this instruction means: suppose we have a register pair, suppose we have a register pair DE, and suppose we have a memory, suppose we have a memory, and suppose here we are having data, and suppose here we are having data, suppose we are having data. So suppose this address location is suppose it is 3001H, this address location is 3001H, and this address location is 3002H. So I told you that this higher byte, that this higher byte will come into higher address location, this lower byte will come into lower address location. Here let me change this data, otherwise you will not be able to differentiate this concept. Suppose it is 2010H, suppose it is 2010H. So how you are going to place it into memory? How you are going to place it into memory? This lower byte data is going to come at a lower address location. Say this is lower, this is higher, and this 20H, it will come at higher address location. It will come at higher address location. So now data is available here. Now data is available here. Now you are going to fetch this data. Now you are going to fetch this data, and you have to bring it into register pair, and you have to bring it into register pair. So here also this lower byte data will come into E register. It will come into lower byte of register pair, and this 20H will come into D register, that is higher byte of register pair, higher byte of register pair. So fine. So this is all about our working. This is all about our function. This is all about our function of this instruction. Now see, coming to the length. Now see, coming to the length. Now coming to the length of instruction. So let me first fill it again. AF, BC, DE, HL, PC, IR, and decoder, ALU, control unit. Okay, fine. Fine. Now if we take this instruction only, if we take this instruction only, if we will take this instruction only, load immediate H. H means we are talking about HL. We are talking about HL register pair, and this is our data. This is our data. So see how you are going to store this instruction into memory. How you or programmer is going to store this instruction into memory. First, programmer will store opcode into the memory. First, programmer will store opcode into the memory. It will take 1 byte space. It will take 1 byte. Now, programmer will store 16-bit data into the memory. Now, programmer will store 16-bit data into the memory. So, how it will be stored? This lower byte data will take a lower address location. it will take a lower address location, and this higher byte will take a higher address location. It will take higher address location. So see how much space is taken. 3 byte. 3 byte. See, 3 byte is taken. So what will be my length of this instruction? My length will be 3 byte. My length will be 3 byte. Are you able to get it? Are you able to get it? See our maximum length of instruction which is possible in 8085 is of 3 byte. Maximum length of instruction which is available in 8085 microprocessor is 3 byte. So you should get it. How you are getting this 3 byte? First is the opcode, and the next two memory location will be occupied by the 16-bit data. So total we are using 3 byte of memory location. We are using 3 byte of memory location. Fine. Now if we talk about the machine cycle, so from here only we can see, from here only we can find out that how many machine cycles are required. See, first microprocessor will fetch the opcode. First microprocessor will fetch the opcode. Then microprocessor will fetch this lower address. Then the microprocessor will fetch this lower byte of data. First microprocessor will fetch this opcode, then microprocessor will fetch this lower byte data, then microprocessor will fetch my upper byte data. So 3 machine cycles will be required. One will be opcode fetch and 2 will be memory read. One will be opcode fetch and 2 will be memory read. See, this I gave you overview. So see, now here I am not going to write step by step, but I am going to verbally explain you. That what all will happen. And how these 3 machine cycles are executed. So fine. See, first first programmer has stored this instruction into memory. So now my PC and reset button is pressed. So my PC will be 0000. Here my some addresses will come. It is suppose 3000. So it will be 3000 3001H, and here it will be 3002H. Fine. Now suppose programmer has fed this instruction into memory, reset button is pressed. Now what will be the status of program counter? It will be 0000H. Fine. Now microprocessor will send starting address. Into the address line. So my this address location will be highlighted. Then microprocessor will send memory read control signal. And now during this time my program counter will be shifted to next address location, that is it will be shifted to 3001H. Fine. Now my opcode will be fetched and it will be brought back into the microprocessor through data line. It will come at instruction register, it will be decoded. Fine. Now microprocessor know that it has to fetch 16-bit address also from the memory. So it will again send memory address 3001H. Now this will be highlighted. Again, memory read control signal will come here. By this time, my program counter will be 3002H. Now my lower byte will be fetched, and from this address bus, it will come. It will come directly into. If I have taken into if I have taken HL register pair, then it will come at the L register. It will come at the L register. It is lower byte data. Now again, microprocessor know that it has to copy another 8-bit data. So it will again send register address 3002H. Now again, memory read control signal will come here. Program counter now will shift to next address location 30003H. Now again, this 60H will be fetched, and it will be brought back into the microprocessor through data line, and it will be stored in LHH register pair. H register pair. So this was all about our working. And by this only I am saying that there are 3 machine cycle: opcode fetch, memory read, and memory read. So if anyone if it is asked in objective, then what will be the number of T states? 4T for opcode fetch, 3T for memory read, 3T for memory read. That is 10 T states are required. 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 I don't think that now you want explanation of T state. I don't think you will want explanation of this T states. You will want explanation of this T states, because what we will get, because see what we will get. If I talk about this only, here we have one opcode fetch. This part we have one opcode fetch. This part we have one memory read. This part we have one memory read. Now for next 3 T states, we will get the same thing here. So it is unnecessary to draw the same thing and waste our time. We can use this time somewhere else, which will be beneficial. So I am not drawing. So I am not drawing this T states. So this was all about our instruction. Load immediate register pair 16-bit address. Load immediate register pair 16-bit address. Now, coming to next instruction, first of all, I want to show you something. I want to show you the importance of this register, the importance of this instruction, the importance of this instruction. What is the importance of this instruction? So we saw that what is the meaning of this instruction? Load immediate register pair 16-bit data, that we have to load this 16-bit data into this register pair. Suppose for example we have an instruction like this: D 2010H. So after execution of this instruction, what will be content of DE register pair? What will be content of DE register pair? It will be 2010H. It will be 2010H. And I told you that how many T states will be required? How many T states will be required? 10 T states will be required for execution of this instruction. Now suppose if we want to store this data, into same register pair, into same DE register pair, but now we want to store this data into D register pair, not by this instruction, but by move immediate instruction. See, by move immediate also we are storing data into memory. But what is the difference? There we are storing 8-bit data at a time into memory, and here we are storing 16-bit data at a time into there we are storing 8-bit data into register. There we are storing 8-bit data into register, but here we are storing 16-bit data into register pair. But here we are storing 16-bit data into register pair. But here we are storing 16-bit data into register pair. But here we are storing 16-bit data into register pair. So now suppose if we want to perform same operation using MVI instruction. Suppose we have MVI D, comma 8-bit data, 8-bit data, and so by using this instruction what we will get? Our D register will have content 20H. Now similarly, if we will have this instruction MVI E 10H, MVIE 10H, then our E register will have content 10H. So if we will combine both, suppose if we will combine both this instruction, if we will combine both this instruction and make a program, this is my program, then the end result will be same only. That is D register pair is having data 2010H. But what is the difference between these two? Here we are requiring 10 T states, but here see, for this we will require 4 plus 3 T states, and for this we will require 4 plus 3 T states, that is total we will require 14 T states. That is 4 extra T states will be required here. 4 extra T states will be required here. That is, if we want to perform this operation, then this is a better solution to us, because less number of T states, that is less time is required, but here more time will be required. And why we are getting this difference? We are getting this difference because by move immediate instruction we are storing 8-bit data into register. We are storing 8-bit data into register, but by this instruction load immediate, we are storing 16-bit data into register pair. We are storing 16-bit data into register pair. We are storing 16-bit data into the register pair. Now coming to our next instruction. That is LDA 16-bit address. Now we will take two important instructions. One is the LDA and another which we will discuss is the STA. These two instructions are very important, which are frequently used in program. So what is this LDA 16-bit address? LDA 16-bit address, it means load accumulator with the data present at 16-bit address. Load accumulator with the data present at 16-bit address. So let's see. Here also we will see it into we have categorized it into four part. That is, first will be the function. Second one will be length. Third one will be machine cycle, and fourth one will be T state, and fourth one will be T state. So coming to function. Suppose we have instruction LDA. Take this 6000H. So here we have microprocessor. Here we have accumulator. Here we have accumulator. Here we have a memory. Suppose this is our suppose this Suppose this is our address location and here content is 20h. Then meaning of this instruction is that we have to load accumulator. We have to load accumulator with the data, with the data whose address location is given here. Whose address location is given here. It is a 16 with STA and LDA. We have 16-bit address as operand. With STA and LDA, we have 16-bit address as operand. For LXI, we had a 16-bit data as operand, but here we will have 16-bit address as operand. So we want to load accumulator with the data whose address is given in our instruction. Whose address is given in our instruction. So this was all about our function. Now we will look into it more details, that how it is happening. We will look into it in more detail, that how it is happening. Now see, coming to the length. Now coming to the length. See, we have LDA 6000H. So first, programmer will store opcode into the memory. Programmer will store opcode into the memory. Then programmer will store lower byte address into memory. Then programmer will store lower byte address into memory. Then programmer will store higher byte address into memory. Then programmer will store higher byte address into memory. So what is our total length? It is also of 3 byte. It is also of 3 byte. See the best form of finding the length is that whatever instructions or program is given to you, you just write it step by step. Suppose after this you had a program where we had another instruction. After this instruction we had suppose b comma 10h. We had b comma 10h, and if we would have been asked to find the length of this instruction, so this part we have completed. Now we will take this part. So here also first opcode will be stored into the memory. And then this data will be stored into the memory. So see, what will be my length? My length will be 3 plus 2 5 byte. So whatever is given into the program, so whatever instructions are given in the program, write it step by step. First one you will get opcode. Second one you will get either data. Data can be two type, 8-bit or 16-bit. And another thing, you can get address. Address is always of 16-bit. By this you will fill this memory location, and then you can count that what is the number of length, what is the length of this program, of those programs. Okay, fine. We will take all these questions. We will take a thorough questions on instructions. We will solve all previous gate exam questions. We will take all previous gate exam questions, ESE exam questions, many more questions we will take, and we will discuss everything. Here I am just forming the base of instruction set. So just listen. So it is a 3 byte. Now coming to the machine cycle. This one is important. 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 So now suppose first let me fill all this thing. This is AF, BC, DE, HL, PC, IR, and a decoder, ALU, CU, all will be connected. All will be connected. This is my starting address. This is my starting address. This is my next address. This will be my next to next address. And somewhere here we will have address location this. Suppose somewhere here we will have address location this, and it's somewhere here we will have address location this. And here we have data 20h. Here we have data 20h. Now see how it will be executed. How it will be executed. So first, programmer will write opcode into the memory. It will write opcode into the memory. Then it will write the lower address. Then it will write the lower address. Then it will write the higher it will write the lower byte address, then it will write the higher byte address. Fine. Now reset button is pressed. Now suppose reset button is pressed, my PC is reset button is pressed, PC is 0000h. Fine. Now my address location 3000h will come at address line. This address location will get highlighted. It will get highlighted. Now memory read. Now memory read control signal will come to the memory. By this time it will become 3001h. Now memory read control signal will come here. Opcode will be fetched. Opcode will be fetched. It will come into the instruction register and it will be decoded. And it will be decoded. Now again microprocessor will send 3001h address into address line. Now this memory location will get highlighted. This memory location will get highlighted. Again memory read control signal will come here. Again memory read control signal will come here. My program counter will shift to next address location. Now my this lower byte address. Now my lower byte address, it will be read. Now this lower byte address. Now my this lower byte address will be read. Now my lower byte address will be fetched. It will be fetched and it will come into the microprocessor through data line. It will come into the microprocessor through data line. Now here there is one important concept. Here there is one important concept. And here comes the role of temporary register. Here comes the role of temporary register. You will say that this lower byte address which is fetched by the microprocessor, if it comes into the microprocessor, then where it will be saved? Then where it will be saved? Where it will be saved? Because here nothing is defined. Here nothing is defined. So it will be saved into the temporary registers. It will be saved into the temporary register. This temporary register WZ, I have told you earlier also that it is not accessible to programmer. It is not accessible to programmer. It is used by microprocessor only. It is used by microprocessor only for internal operation. So fine, this lower byte will come into temporary register. It will come into temporary register. It will come into temporary register. It will come into lower byte of temporary register. Now fine, again our address 3002h will come into address line. This location will get highlighted. Again memory read will come. Again memory read will come. It will shift to next address location. Now again this higher byte address will be fetched. higher byte address will be fetched, it will come into data line, it will come into data line, and again it will come into the temporary register, and again it will come into temporary register, and again it will come and it will get saved or stored into temporary register, So fine, now we have fetched this now we have fetched the opcode, as well as we have fetched this 16 bit address from memory. We have fetched this 16-bit address from memory. Now see, now what we have to do is that now we have to fetch this data. Now we have to fetch this data which is at memory location 6000H, and we have to bring this data into the microprocessor and store it into accumulator, So now see what microprocessor will do. It will now again send address into the address line. This time it will send address 6000H. It will send address 6000H into address line, because from where we have to fetch data? We have to fetch data from the address location 6000H, which we have already fetched from memory, and stored it into temporary register, So again this address comes into address line. Now my this memory location gets highlighted. Again memory read control signal will come here. My PC will change to 6001H. Now again this data will be fetched. It will come into the data line. And now it will be saved into accumulator. So this all was the process. Of microprocessor while it is executing this instruction. So this was all the process of microprocessor while it was executing this instruction. So if we talk about the machine cycle, what will be our machine cycle? First is the opcode fetch. Then comes memory read for lower byte address. Then again we have a memory read for higher byte address, and then again we have a memory read for fetching data. See, one memory read for this, and one memory read for this. So we have one opcode and 3 memory read. So if it is asked in objective, so what will be my T state? For opcode fetch, we have 4T. For memory read, 3T. If we will add all this thing, 7, 10, 13T. 13 T states are required. For LDA 16-bit address. 13 T states are required for LDA 16-bit address. Now if we talk about the calculation of T states, so here again I am not going to draw it, because it will be same. See, the main portion was first two opcode fetch and memory read or memory write. These two are the main which you have to understand, and after that you can just simply copy this part based upon whether it is memory read or memory write. You will just copy this part based upon whether it is memory read or memory write. So here in this instruction, in the MVI instruction, we saw that this was the opcode fetch part, this was the memory read part. Now in LDA 16-bit address, we have 3 memory read, so we have to copy 2 more here. So now you have to copy 2 more here, so that your total T states will become 13T. So I'm not going to do it for you. You can do it on your own. Now the concept is clear to you. Now you can draw it on your own. on your own. Now you can draw it on your own. So this was all about the functioning of LDA 16-bit address. Now we will look into the functioning of STA 16-bit address, which is just opposite of LDA 16-bit address. So let's see it. Now coming to next instruction, which is STA 16-bit address. STA 16-bit address. You can say it is just an opposite of LDA. It is just an opposite of LDA. In LDA, what we were doing? In LDA, what we were doing? We were loading accumulator. We were loading accumulator with the data whose address location was given in the instruction. Whose address location was given in the instruction. And in STA, what we will do? In STA, what we will do? We will take the content of accumulator. We will take the content of accumulator and we will store it into memory. And we will store it into memory whose address location is given in the instruction. Whose address location is given in the instruction. Whose address location is given in the instruction. That is, suppose if we have STA 6000H, fine. Here we have microprocessor. Here we have accumulator whose content is suppose 10H. Whose content is suppose 10H. Now we have memory. Now we have memory. Now we have memory. Now we have to store this content of accumulator into memory. We have to store this content of accumulator into memory whose address location is given in the instruction. 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 So it is just reverse of LDA. In LDA we were fetching this data, putting it here, and in STA we are fetching the data from here and putting it here. And the address location from where we are fetching or we are writing, it is given in the instruction. It is already given in the instruction. It is already given in the instruction. So its function is clear. Now coming to its length, it will also be a 3-byte instruction. It will also be a 3-byte instruction, 1 byte for opcode, 2 byte for addresses. It is clear from here. Now coming to the machine cycle. Now coming to the machine cycle, here everything will be same. Here let's see again. Let's see it again. I can compare it with previous one also. But okay, let's see it again. Suppose we have AF, BC, DE, HL, PC, IR, ALU, TU. Starting addresses. This. Then we have this. Then we have this. Then we have this. Fine. So see, if I talk about the working, first programmer will store this instruction. First programmer will store this instruction. This all we have seen. No need to repeat it again. Fine. Then the reset button will be pressed. Then the first address which microprocessor will originate is 3000H. Then memory read control signal will come here. Opcode will be fetched. It will be brought into the instruction register and it will be decoded. Now again, the second address 3001H, it will come into the address line. It will be highlighted. Now again memory read. Now again lower byte address will be fetched. It will be brought into the temporary register. It will be brought it will be brought into temporary register. It will be brought into temporary register. Now again the next address will come here. This location will get highlighted. Again memory read, this address, higher byte address will be fetched and it will be brought into the temporary register. It will be brought into the temporary register. Now again microprocessor will originate this address 6000H, which is stored in the temporary register. Now this memory location will get highlighted. Now what will happen? Memory read will take place or memory write will take place. So what I told you, here we have to store content of accumulator into memory. Here we have to store content of accumulator into memory. So now memory read control signal will not come. Now memory write control signal will come here. Now memory write control signal will come here, and suppose content of accumulator is 20H. So this 20H will be copied here. It will be copied here. So if we talk about the machine cycles, it will be opcode fetch, memory read, and memory write. If we talk about the T states, 4T, 3T, 3T, 3T. It is also 13T. It is also 13T. It is also 13. It is also 13T. It is also 13T. Now, if we will come to the calculation of T states from this descriptive portion, for objective we have seen it is 13T, but if we want to see it from here, then see everything will be same. This opcode fetch will be remain the same. This memory read will remain the same. Here again you will have one memory read, then again you will have one memory read. In LDA we had one more memory read, but in STA, in this place we will have memory write. So see what differences we have to make there. See, I am this part. I am taking the last part. Memory write part. I am going to show you here. The entire thing you can draw it on your own. Now you are conversant with it. I am not going to draw the 13T. I am only going to take up the last 3T state, where instead of doing memory read, we are doing memory write. So for that time, our memory write control signal, it will be enabled. Memory write control signal, it will be enabled, and it will be enabled for T12 and T13. It will be enabled for T12 and T13. Fine. And if I talk about the read, read is not taking place. So if I talk about the read bar control signal, then my read bar control signal will be high. That is, it will be disabled. So now we will take NAND combination of this. So instead of memory read, we are we are going to get memory write. Only this few changes you have to do in our last 3T states for STA as compared to LDA. Rest you can solve it on your own. The last portion I have showed you. So again, the total T states will be 13. So this was all about our instruction STA. It is easy. Now you can see that once you get the flow from the starter instructions, now see how things are getting easier for you. You can you just have to know the function of instruction. And now you have so much in-depth knowledge of the processing of microprocessor that after knowing the function, you can easily find out the length of instruction. you can easily find out the number of machine cycles involved, and from there you can easily find the number of T states involved. And if a question is asked in conventional to draw it, then you can easily draw it also. So now I think you are getting grip on the instruction set. So let's move forward. Now coming to next instruction, that is LDAX register pair. Now coming to next instruction, that is LDAX register pair. So what it says, it is its function is load accumulator with memory content whose location is specified by content of operand, that is register pair. Load accumulator with memory content whose location is specified by content of operand, that is register pair. So let's see. This also we will look into in four parts. This also we will look into in four parts. First will be the function. First will be the function. First will be the function. Second will be length. Second will be length of instruction. Third will be machine cycles involved, machine cycles. And fourth will be calculation of T states. Fourth will be calculation of T states. So see, coming to the function part. Coming to the function part, suppose we have instruction like this. LDAX, LDAX B. Here also LDAX is associated with register pair. LDAX is associated with register pair. So in instruction, if B is given, then it is actually BC register pair. Then it is actually BC register pair. Now suppose this is my microprocessor. This is my microprocessor. This is my BC register pair. This is my BC register pair. And content of BC register pair is something 5010H. Content of BC register pair is something 5010H. Fine. Now suppose this is my memory. Suppose this is my memory. And here we have a address location 5010 somewhere in the memory, and its content is 10H, and its content is 10H. And in this microprocessor we also have, and in this microprocessor we also has a accumulator. We also has a accumulator. We also has a accumulator. Now see, what is the function of this register instruction? What is the function of this instruction? Accumulator has to be loaded. Accumulator has to be loaded with a data which is residing in the memory. With the data which is residing in the memory, whose address location is content of register pair, is content of register pair. That is, we want to load accumulator. We want to load accumulator with the data which is residing in memory, with the data which is residing in memory, and whose address location is content of register pair, is content of register pair, is content of register pair, is content of register pair. So what will happen at the after execution of this instruction? This data 10H will be copied. this data 10H will be copied into the accumulator. This data 10H will be copied into the accumulator. So now see, we also saw LDA. We also saw LDA 16-bit address. We also saw LDA 16-bit address. Here also we were loading accumulator with the data present at 16-bit address. Means here the address of data which is to be loaded into the accumulator is directly given in the instruction. So we also call this as an example of direct addressing mode. So we may also call this instruction as an example of direct addressing mode. Direct addressing mode, where the address of data, which is to be loaded into the accumulator is directly given in the instruction. But here see, the address of data which is to be loaded into the accumulator directly given in the instruction? No, it is not directly given, but it is indirectly given in the form of content of a register pair. It is indirectly given in the form of content of a register pair. So such instruction is an example of indirect addressing mode. Such instruction is an example of indirect addressing mode. Such instruction is an example. Such instruction is an example of indirect addressing mode. See, we will look into the addressing mode in details. But just here when we were discussing these two instructions, so I thought of giving you a small idea of direct and indirect addressing mode, but we will look this addressing mode in details. Don't worry. So this was our function. So this was our function of LDX register pair. So this was our function of LDX register pair. Now if we talk about the length, then the programmer will first feed the opcode of this instruction. Programmer will first feed the opcode of this instruction. After feeding the opcode of this instruction, nothing is required to be fed into the memory by the programmer. So it is also 1 byte instruction. It is also 1 byte instruction. So its length is 1 byte. So its length is 1 byte. Now see, coming to the machine cycles, I think by now you must be knowing that what all machine cycles will be involved here. So just quickly look into it. Let me fill all these boxes. AF, BC, DE, HL, PC, instruction register and decoder, ALU, CU. Okay, fine. Let's suppose here the content of BC is 40 10H. Content of BC is 40 10H. Now see how the microprocessor will execute this instruction. First, the programmer will load this opcode of this instruction. Programmer will load opcode of this instruction. It is loaded. Then reset button will be pressed. Program counter will be 0000H. Fine. Now microprocessor will originate initial address Initial address will come into the address line. Initial address will come into the address line, and this address location will be highlighted. This address location will be highlighted. Now microprocessor will send memory read control signal. Now microprocessor will send memory read control signal. This opcode will be fetched, and it will be this opcode will be fetched, and this will be brought back into the microprocessor through data line. This opcode will come at instruction register, and it will be decoded, by this time our program counter will be 3001H. Now after decoding it, microprocessor knows that it has to load accumulator with data which is present in memory, and whose address is the content of BC register, Now content of BC register is 4010H. So microprocessor will send this address to the memory through address line. Microprocessor will send this address, or it will place this address on the address line. Now when this address is placed on address line, then this memory location will get highlighted. Then this memory location will get highlighted. Now again microprocessor will send memory read control signal. PC will become 4011H, and now this data whose at memory location 4010H will be read or fetched, and it will be brought back into the microprocessor at accumulator through data line. So this was all our working. So what all machine cycles are involved? First will be opcode fetch, and second is the memory read. First is the opcode fetch, and second is the memory read. So it will be opcode fetch. And it will be memory read. Now coming to T states, again it will be 70. Now coming to T states, again it will be 70, and we are not going to draw it again because we have already seen the timing diagram for opcode fetch and memory read. We have already seen the timing diagram of opcode fetch and memory read. So this was all about our instruction LDX register pair. Now coming to next instruction. STX register pair. So it is just opposite. Of LDX register pair. Here, what it says: store content of accumulator with memory content is specified by content of operand, that is register pair. Suppose again we take an example. Suppose we have a BC register. Whose content is 4010H. Okay, fine. Now suppose we have a accumulator. Whose content is 10H. Suppose we have a accumulator whose content is 10H. Suppose we have an accumulator. Accumulator whose content is 10H. So after execution of this instruction, this 10H will be copied into the memory. And where it will be copied? It will be copied at a address location which is content of BC register pair. It will be copied at a address location. It will be copied at address location which is content of BC register pair, which is content of BC register pair, which is content of BC register pair. So in previous one, we were fetching data from memory into accumulator, and in this one, we are loading data of accumulator into memory. We are loading data of accumulator into memory, and address location is the same, that is content of register pair. Address location is same, that is content of register pair. So again, if we talk about this four items, then function I have told you, length it will be again 1 byte. Machine cycle, in place of, if I talk about machine cycle, then in place of memory read, I think you must be knowing it now, it will be memory write. It will be memory write. In place of memory read, it will be memory write, and T states again it will be 70. And T states again it will be 70. Again it will be 70. So this was all about our two instructions, LDX register pair and STX register pair. Now, before we start next instruction, there's an important observation which you should keep in mind. There's an important observation which you should keep in mind, and sometimes questions, objective questions may come based on this observation, and sometimes objective questions may come based on this observation. So let's see. See, I told you that stacks is associated with register pair. But what all instructions are available to us? Stacks B, that is BC. Stacks D, that is DE. These both are available. These both are available. But we have another register pair, that is HL. So stacks H, or we can say HL. Is this instruction available? No, this instruction is not available. Similarly, if I talk about LDX, then LDAX B, that is BC, or LDAX D, that is DE. These both are available. These both are available. But if we talk about another third register pair, that is LDAXH or HL, is this available? Is this available? No, this is not available. This instruction is not available in 8085 microprocessor. Then you will say that why it is so. It is so because we are already having two instructions, and we have already read about this two instructions, which is doing exactly the same work, which is doing exactly the same work which this both instructions would have done respectively, and by using or by executing this instruction, we are not saving any time. If we compare with this two instruction. Here also 70 states would have been required, and here also move m comma a and move a comma m, 70 states are required. So there was no purpose of using two instruction for the same purpose. So there was no need of using two instructions performing or executing same purpose. So this is an important observation. If you get a question in the exam, that whether this are LDXH or LDXH are valid instructions, then you will so say no, it is not valid because they are not available. Because they are not available in the 8085 microprocessor, because STXH work is done by move M comma A, and LDXH, that is HL register pair work, is done by move A comma M. We have seen both this instruction in details, so I am not going to explain you again here. I am just going to give you an important observation or concept which I have given you. Now I will take one step more based on this instructions. uh, there is one more observation. There is one more observation, and that is, see, we have instructions like move A comma M, move B comma M, and similarly all C comma M, D comma M, H comma M, L comma M. Similarly, we have move M comma A, move M comma B, and similarly we will have rest all. Then is move M comma M a valid instruction? Is move M comma M a valid instruction? So in 8085, move M comma M is not a valid instruction. Rest all these things are valid, but move M comma M is not a valid instruction. So in this slide, I have given you two important observations, and this both observations are important for your objective exams. They are important for your objective exam. Now coming to next instruction, that is in 8-bit address, and then we will look into out 8-bit address. These two instructions are very important. These two instructions are very important because till now we were discussing interface between microprocessor and memory. Till now we were discussing interface between microprocessor and memory. But now we will discuss interface between microprocessor, memory, as well as interface between microprocessor and input-output device. So it's going to be a new thing for you. And let's see how microprocessor interface with input-output device using in instruction and out instruction. Using in instruction and out instruction. So some of the differences which we should know before we start the instruction. So when microprocessor interfaces with input output device, then 8-bit addresses are used. 8-bit addresses are used. 8-bit address is used. See, this all we have discussed in details when we were studying memory mapping. So I'm not going to explain you again, but I'm just going to give you an overview. You can refer my those sessions. 8-bit address, and when microprocessor was interfacing with memory, then 16-bit address was required. 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 So if I am telling that if microprocessor interfaces with input-output device, then 8-bit address is required. So if we take 2 to the power 8, that is 256 input as well as 256 output devices. Input, 256 input, and 256 output device, and 256 output device can interface with microprocessor, can interface with microprocessor, fine, can interface with microprocessor. And if it is 8-bit, what will be its starting address? Its starting address will be this, and its ending address will be this. This all we have seen, but here I am just giving you an overview. So 00 to FFH. So 00 to FFH. Range of addresses of input output devices. Range of addresses of input output devices. So coming to our in instruction, in 8-bit data, its function is access the data from 8-bit port address of input into accumulator. So see, this part also we will discuss in four subparts. First one will be function. First one will be function. Second one will be length. Second one will be length. Third one will be machine cycle. Third one will be machine cycle. Then we have T steps. Then we have T steps. So let's see here. Let me draw let me draw an input device here. Let me draw an input device here. See, I am drawing this input device, so don't think that it is some integrated part of microprocessor and memory. Microprocessor is separate, memory is separate. Microprocessor and memory are connected with data lines, address lines, and control lines. And now I am adding one input device also. I am adding one input device also. Let's suppose it is like this. It is like this. It is a input device. It is a input device. It is input device. Here we have seen. Here we have seen the control signal. Here we have seen control signal. Input output read bar. Input output write bar. Here we have seen the enable pin. Here we have seen the enable pin. Here we have a NAND gate. Here we have a NAND gate. Here we have NAND gate. Here we have a NAND gate. Here we have a NAND gate. Here we have a NAND gate. And here we will have data lines. 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 Let's connect it with this data line. Let's connect it with this data line. And this will be our address line. Connect it with address line. Connect it with the address line. Connect it with address line. So this is some rough sort of input device which I have drawn here for understanding purpose. For understanding purpose. So let's see first how our instruction is working, and then we will fill, and then we will come into these four subparts. Then we will come into these four subparts. So let's see the working. So we have instruction this, we have instruction this. So again, the programmer will first, the programmer will first load this instruction into the memory. The programmer will first load this instruction into the memory. It will load this instruction into the memory. So first opcode will come. We are having a separate opcode, a predefined opcode for in. So opcode will come. then the programmer will load this 40H address here. This 40H will be loaded here. This 40H will be loaded here. Fine. This 40H will be loaded here. Fine. Now again, reset button will be pressed. PC will become 0000H. Now, if I complete this also, AF, PC, DE, HL, PC, instruction register and a decoder, ALU, CU. Fine. Now microprocessor will place initial address 3000H on the address line. This location will be highlighted. Then memory read control signal will be generated. Memory read control signal will come here. It will fetch the opcode, and through data line it will come into the instruction register and it will be decoded. By this time the status of program counter will be 3001H. Fine. Now again microprocessor will place address 3001H on the address line, because now it wants to fetch the address of input device. Now again memory read control signal will come here. This address 40H will be fetched, and through data line it will come inside the microprocessor. Now inside the microprocessor, where it will come? It will again come, as I told you, in the temporary register. It will come in the temporary register. 40H will come here. That is at the lower byte, of temporary register. But it is the functioning of microprocessor that this 40H, which was copied into the lower byte of temporary register, it will be copied into the higher byte also. That is, it will be copied into W register also. First, when it will come from the memory, it will be copied at Z register, lower byte, and then it will be copied to the higher byte, that is W register. So content of WZ register pair will be 4040H. Content of WZ register pair will be 4040H. 4040H. Fine. Now comes the important part, which we will learn first time. Because earlier we were dealing with the microprocessor and memory, but now the interface between microprocessor and input-output device will start. Now interface between microprocessor and input-output device will start. So now microprocessor will place 4040H address onto the address line. It will place 4040H address onto the address line. It will come here. It has only 8 lines. Because I told you that input output device has 8-bit addresses. So 40H will come here. Now my this input device will be highlighted. Or it will be enabled. Now microprocessor wants to fetch their data 10H. From the input device. So again it will send. This time it will send input output read control signal. This control signal will come here, and now the data 10H will be fetched. Or read, and through data lines it will come inside the microprocessor, and it will be placed inside accumulator. So I will repeat it again from the temporary register. The content of temporary register is 4040H. Now microprocessor will place this 4040H into the address line, because address of memory, because address of input output device is 40H, because address of input device, not output device, address of input device, 8-bit address of input device is 40H. So it will place 4040H into the address line. 40H will come here, input device will be enabled. Now microprocessor wants to read data 10H from the input device, so it will send input output read bar. Input output read bar will come here. It will read data 10H, and this data through data line will come inside the accumulator. Keep one thing in mind, that whenever that when microprocessor deals with input output device, then the data is always transferred between accumulator and input output device, between accumulator and input output device. That is, if data is coming from the input device, it will be stored at accumulator, and when data is to be copied into the output device, and when data is to be copied into the output device, then that data will be taken from the accumulator. That is, the register which interfaces with input output device is accumulator. Very important for your objective point of view. So this was our working. Now see, if we want to fill this, then this, what is the length? Length is 2 byte. Length is 2 byte. Yes. Length is 2 byte. Length is 2 byte. Sorry. This was the function. Function I have discussed with you. An elaborate discussion has been done just now. So function is clear. Now coming to length, it is 2 byte. Now coming to length, it is 2 byte. Now coming to machine cycles, see what all machine cycles are involved. First was the opcode fetch, then was the memory read, and then was our input output read. So opcode fetch, then memory read, then input output read, if I want to write it in words, then input output read. Now see, coming to t states, what will be number of t states required? 4t. 3t. For input output read write also it is 3t. For input output read write also it is 3t. So it is total 10t. We will draw these t states. I will draw these t states because first time we are going to draw t states for input output. For first time we are going to draw t states for input output. I will draw it, but I will draw it first after discussing output instruction also. Not output instructions, out instruction also. So I hope this in instruction is clear to you. Fine. Now see, again coming to the out instruction. Now here again, suppose we have a output device. Here we are having control signals. Here we are having control signals. Here is my enable pin. This is 8 line. It will be connected with address line. This is my data line. It will be connected with the data line. So this is my output device. Suppose this is my output device. It is my output device whose address, suppose it is 40H. Its address is 40H. Its address is 40H. Now see what is the function of this out 8-bit data. It is going to load content of accumulator into 8-bit port address of output. Into 8-bit port address of output. In the in instruction, what we saw was we were loading accumulator. We were loading accumulator with the data which was present in the input device, and now we will copy content of accumulator. Now we will copy content of accumulator into the output device whose address location is given, whose 8-bit address location is given, whose 8-bit address location is given. Now let us see it quickly how it will work. Again programmer will load the output of out instruction. Then programmer will load the 8-bit address of output device. It will load the 8-bit address of output device. So again length will be 2 byte. Now microprocessor will first fetch the output. Then microprocessor will fetch the 8-bit address of output device. Now this address will come into the temporary register. Z, it will be copied to W. So the content of WZ will be 40H. Now this 40H will come here. Now my output device will be enabled. Will be enabled. Suppose we have accumulator whose content is 10H. Now microprocessor wants to copy the content of accumulator into output device whose 8-bit address is 40H. So now input output write instruction control signal, input output write control signal will be originated by microprocessor. Input output write control signal will be originated by the microprocessor. It will come here, and now the data 10H. Now the data 10H which was in accumulator will come from the data line, and it will get stored in our output device. So if we talk about the machine cycle, we first had output fetch, then we have memory read, and then we had input output write, and then we had input output write, and so we had opcode fetch, machine cycle, memory read, and input output write. So what will be my number of T states? Again it will be 10T. So this was all the functioning of in instruction and out instruction. We discussed both functions. We discussed length. We discussed number of machine cycle involved. We found out the number of T states. Now we are going to draw the timing diagram of input and output device. Now we are going to draw timing diagram of input and output device. Now coming to calculation of T states. So first we will look into instruction. Initial address is 3000H. Instruction is in 40H. So first we will start with higher order address bus. So we know that a higher order address bus will be enabled for 3 clock pulse, or for 3 T states, and it will hold higher byte of initial address. Fine. Now coming to lower order address bus. A7 to A0. So it will be enabled for one T state. It will be enabled for one T state, and it will contain lower byte of initial address. It will contain lower byte of initial address. These all things we know very well. Now coming to ALE. Now coming to ALE. So it will also be high for one T state. It will also be high for one T state, and during this one T state, lower order address bus acts like a address line, and after that it will act like a data line. So fine. Now coming to input output and memory bar. So for opcode fetch, microprocessor will interface with memory. So it is a active low control signal. So this will remain enabled. That is, it will remain active low. It will remain active low because microprocessor is interfacing with memory. Now if we talk about read bar control signal, if we talk about read bar control signal, then opcode fetch operation will take place in the initial T states. So this process opcode fetch starts from T2 to T3 T states. Memory read will take place from T2 to T3 T states. T2 to T3 T states. So it is also a active low control signal. So it will remain active low for T2 to T3. T2 to T3. Now if we talk about memory read. Now if we talk about memory read control signal, then it is a NAND operation of both this. It is a NAND operation of both this. So memory read control signal will be enabled. It will also be enabled. It will also be enabled for two T states, T2 and T3. It will also be enabled. It will also be enabled for two T states. It will also be enabled for two. It will be enabled for two T states, that is T2 and T3. So fine. So during this opcode fetch will take place. Opcode fetch will take place. So the opcode of instruction. So opcode of instruction, that is in, will be copied into lower order address line, will be copied into lower order address line, and it will come inside microprocessor, and it will come inside microprocessor, and it will come inside microprocessor. If we talk about write bar, if we talk about write bar control signal, then nothing is written inside the memory, so it will remain high. That is, it will remain disabled. It will remain disabled. All these things takes place for start in three T states, but for opcode fetch, one more T state is required because microprocessor needs to decode it. So opcode fetch will continue for four T states. It will continue for four T states, and during this extra one T states, it will be at high impedance. It will be at high impedance. So this is all about opcode fetch. This all we have seen. This all we have seen in details, and now we are fully expert in it. But still, I am just reminding you in case you have missed something or in case you have not understood anything. Our main focus will be the latter part. This all things we have seen. So this is all about opcode fetch. 4 T states. Now second machine cycle is memory read. Second machine cycle is memory read. So now again, this higher order address line will be enabled for for 3 T states. For 3 T states. Fine. And now the next address is 3001H. So it will again have higher byte of address 30H. 30 30 30H 30H. Fine. Now if I talk about the lower order address line, then it will be again enabled for 1T state. It will again be enabled for 1T state, and it will hold lower byte of 3001H, lower byte. Now if I talk about ALE, then again it will be high for 1T state. It will be high for for 1T state when this lower order address line acts like an address bus, If I talk about input output memory bar, so now operation is still happening between microprocessor and memory, so it will be low. If I talk about read bar, then again read bar will be enabled for T6 and T7. Read bar will be enabled for T6 and T7. If I talk about memory read control signal, then it will also be enabled for T6 and T7. It will also be enabled for T6 and T7 because it is a NAND operation of this two. If I talk about write bar control signal, then it will remain high, disabled. And after this memory read, what will happen? This address of input device, will be copied into the data bus. It will be copied into the data bus. It will be copied into the data bus. It will be copied into the data bus. Fine. It will be copied into the data bus. It will be copied into the data bus. It will be copied into the data bus, and it will be brought back into the microprocessor. Fine. This both machine cycles we have already seen. Now the third one is the new one for us, because now it is input output read. So see how it will take place. So see how it will take place. So see. So first is the higher order address bus. So it will be again enabled for 3T state. What will it contain? It will contain address. It will contain address 40H. Because we have discussed these things earlier also, that this 40H will come into lower order address bus. But same thing is copied to higher order address bus also. These all things we have discussed. In details. Now if I talk about lower order address bus, then it will also have 40H. If I talk about ALE, then ALE will work normally. That is this. So ALE will work normally, and it will be low, because in this case there is no role of ALE. Because we don't require any multiplexing between higher order address line and lower order address line. Now this one is important. If I talk about input output memory bar, now microprocessor is communicating. With input output. So this will be high now. Now microprocessor is communicating with input output, so this will be high now. Now if I talk about the read bar control signal, so again, now if I talk about the read bar control signal, so again it will be low for T9 and T10. 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 Now if we talk about memory read control signal, so now there will not be memory read control signal. What we will have? We will have input output read control signal. We will have input output read control signal. This time we will have input output read control signal. This time we will have input output read control signal. So now, as we have discussed it earlier also, see how will be the arrangement of it. See how will be the arrangement of it. This is NAND gate. This is NAND gate. This is NAND gate. Here we will have input output. Here we will have input output, and here we will have read bar. So there will be an inverter here. Here there will not be any inverter as we saw during memory operation, but here we will have an inverter. So see, for T9 and T10, this is 1, and for T9 and T10 this is 0. So 0 after inverter will become 1, 1, 1, output will be 0. We want 0 only because it is an active low control signal. So input output memory bar, it will also be low for T9 and T10. It will also be low for T9 and T10. And during this, what will happen? The content of input device, the content of input device, the content of input device will be loaded into data line. It will be loaded into data line, and it will be brought into the microprocessor. It will be loaded into data line, and it will be brought into the microprocessor. If I talk about the write bar control signal, then no write-in is done, so it will remain disabled. So total T state required is 10T. So this is the complete operation. So now you have seen interface with microprocessor and memory, as well as you have seen an interface between microprocessor and input output device, and you have seen calculation of T states in both these cases. And now I think that you are fully comfortable with this T states diagram, and you can solve any T state diagram of any instruction or even any program. Not only instruction, you can draw T state diagram for any program also, if it is given in the exam. You have seen the typical and the complex one. In exam you will get very simple. I will take 1-2 example of previous ESE questions which was asked in conventional, and you will see that so simple questions were asked there. So this was all about T state diagram of in instruction. Now suppose here only if I talk about the out. Now here only if I talk about the out instruction. So what will be the difference? See, everything will remain same. This two part is already we have seen it will remain same only. If we talk about this one, then everything will be same. Only difference will be this. I am talking about out. So now if I talk about this for out, this RD bar, we are not reading anything from memory, but we want to write it into memory, so it will remain high. And in this case my write bar control signal, in this case my write bar control signal. Now if I this one, my write bar. Now in case of out operation, we want to write data into the output device. We want to write data into the output device, and this write process will be for T9 and T10. It will be enabled for T9 and T10. That is, read bar control signal will be enabled for T9 and T10, for T9 and T10. And similarly, now if we will refer this one, now we will refer this input output. Now we will refer this input output, this diagram, input output, and now write bar. Now write bar. In case of here, in case of this read, in case of this read, we will write, we will write. So 1 0 T9 T10 1 0, so we will get 0 here. So here we will get input output. Here also, if we will want to change it, so we will get it into input output write bar, input output write bar. So this will be our T state diagram for out instruction. This will be my T state diagram for out instruction. So this was all about my T state diagram for in instruction as well as for out instruction. I hope this is clear. Now coming to next instruction, that is LHLD 16-bit address. Next instruction is LHLD 16-bit address. Its meaning is load H and L register direct. Load H and L register direct. What is its function? Load content of memory location. Load content of memory location pointed out by 16-bit address, pointed out by 16-bit address in register L, and load content of next memory location in register H. So let's see it in details. Let's see it in details. This also we will cover in 4 parts. First one will be function. First one will be function. First one will be function. Second one will be, what is our second one? Length. Yes, second one is length. Third one is number of machine cycles. Third one is number of machine cycles. And fourth one is number of T states. Fourth one is number of T states. So now coming to the function. Now coming to the function. Now coming to the function. Suppose our instruction is 3000H initial address LHLD and 16-bit address and 16-bit address. So suppose we have a microprocessor. Suppose we have a microprocessor in which we have HL register pair, in which we have HL register pair, in which we have HL register pair, and suppose here we have a memory, and suppose here we have a memory, and suppose here we have a memory, and suppose here we have a memory. Now suppose this is our address location 2010H somewhere in the memory. This is our address location 2010H somewhere in the memory, and this is 2011H. 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 Suppose data at 2010H is 20H and data at 2011H is 10H, or take it as 50H, or take it as 50H, or take it as 50H. So meaning of this instruction is that this data, that both this data has to be copied into the HL register pair. Both this data has to be copied into the HL register pair with 20H will be copied in L register, and 50H will be copied in H register, because this is at lower address, so it will be copied to the lower register, that is L, and this is at higher address, so it will be copied at higher register H, means here also we are following the memory rule which we have discussed. Now, where to take this data? From where to take this data? Where this reference is given, where the reference of its location is given. It is given here. LHLD. This is 16-bit address. So data which will be copied in register L, will be given with the instruction, and the data which will be copied in instruction H, in register H, and data which will be copied in register H will be the address location, will be the next address location to this 16-bit address, will be next address location to this 16-bit address, So I hope this is clear. LHLD 16-bit address. HL register is to be loaded. With the data which is present at this address location, as well as with the data which is present at next address location to this, or plus one address location to this, So my function is clear. Now if we come to the length, if we talk about the length of this instruction, if we will talk about the length of this instruction, then see again, the microprocessor, suppose this is 3000, H. So microprocessor, now the programmer will load opcode of this instruction. And then programmer will load this 16-bit address, into the memory. This 16-bit address into the memory. This 16-bit address into the memory. So it is a 3-byte instruction. 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 Now coming to the number of machine cycles which will be involved. So let's see it. PC, instruction decoder, ALU, and CU. Now see, first the reset button will be pressed, then the initial address will be loaded in the address line by the microprocessor. This will get highlighted. This memory location will get highlighted. Now microprocessor will generate memory read control signal. Now microprocessor will generate memory read control signal. This opcode will come into the microprocessor and it will be decoded. Now next address location will be put into the address line, will be latched into the address line. Now again, this address location will get highlighted. Now again, memory read command will be given by the microprocessor, and this address get latched with the data line, and it will come into the temporary register, and it will come into the temporary register. It is a lower address line, it is lower address, it is lower address, so data of this will be stored into Z register, and again the next address will be latched into the address bus. Again memory read command will be given, and this data at higher address will be copied into W register, Now microprocessor will now send this address, into the address bus. Now this address location, will be highlighted. Now again memory read command will be given by the microprocessor. Again memory read command will be given to the microprocessor, and this data will be read, and it will be copied to register L. Now again next instruction to 4010H will be latched with the address line. Now this memory location will get highlighted. Now again microprocessor will send memory read command, and this data 30H, which is at a higher address, will get latched with the data line, and it will be copied into register H, So the content of HL register will be 3020 3020H. It will be 3020H, and address of 20H is 4010H, which was given in the instruction, and address of 30H is address 1 plus of 4010H, that is 4011H. So number of machine cycles involved will be opcode fetch, memory read, then again memory read, then again memory read, then again memory read, and then again memory read. That is five machine cycle, 1 opcode fetch, and 5 memory read. So if we talk about the number of T states, then 4T plus 3T plus 3T plus 3T plus 3T, 7, 10, 16. 16 T states will be required. So length of this instruction is 3 byte. Number of machine cycle involved is 5, and number of T states required is 16T. I'm not going to draw the T state diagram again, because it is simple. We are getting 1 opcode fetch, and we will get 4 memory read. So this all we have already seen. So this is all about LHLD. Now coming to next instruction, that is SHLD 16-bit address. It is just opposite of LHLD. What we saw in LHLD was that we were loading HL register pair. From data which was present at a 16-bit address given in the instruction, and 1 plus 16-bit address which was given in the instruction. Now what we will do in SHLD is that we will write we will write content of accumulator. We will write content of accumulator. We will write content of accumulator into memory, into memory, into memory. At which location? At which location? At memory location or memory address which is given in the instruction. At memory address which is given in the instruction, and 1 plus memory address which is given in the instruction, and 1 plus memory address which is given in the instruction. That is, suppose if this is my SHLD, this is my SHLD, this is my SHLD. Suppose content of HL is 2050. Fine. 2050. So what is meaning of SHLD? We have to store content of accumulator into memory. We have to store content of accumulator into memory. So first this 50 will be stored at a lower address. This 50 will be stored at lower address, and this lower address is given in the instruction, and we will load 20 into higher address, which is 1 plus the address which is given in the instruction, which is 1 plus the address given in the instruction. So this is only written here. Store H and L register direct. Contents of register L are stored in the memory location specified by 16-bit address in the operand, and the content of H register are stored in the next memory location by incrementing the 16-bit address of operand, by incrementing the 16-bit address of the operand. So function is clear. If we will talk about length, length will be remains the same. It will also be 3 byte as that was of LHLD. If I talk about machine code, then you can correlate now. Opcode fetch will be there. Opcode fetch will be there. Memory read will be there. 2-time memory read will be there to read the 16-bit address, and then we will have memory write. In LHLD we were having a memory read. In LHLD we were having memory read because we were reading memory or fetching content of memory and loading it into HL register pair. But now we are copying content of HL register pair into memory. So it will be memory write, memory write. If I talk about number of T states, then 4T, 3T, 7T, 3T, 10T, 3T, 13, 3T, 16. It will come out to be 16 T states. It will come out to be 16 T states. I am not going to the drawing of T states because this all part we have already seen earlier also. So this was all about our instruction SHLD. So this was all about our instruction SHLD. Now coming to next instruction, that is PCHL. Coming to next instruction, that is PCHL. What is its function? Load a program counter with HL contents. Load a program counter with HL contents. Content of H are placed as higher order bytes and L as lower order bytes. Content of H are placed as higher order bytes and L as lower order bytes. Consider, let us consider we have program counter, we have Let us consider we have program counter and its content is 2010H. Its content is 2010H. Its content is 2010H. And we have a HL resistor pair. We have a HL resistor pair whose content is 4050H. 4050H. Now we want to change flow of program. Now we want to change flow of program. We want program counter to shift at address location 4050H. We want a program counter. We want a program counter to switch to address location 4050H. Then in that case we can directly use this instruction. Then in that case we can directly use this instruction in which content of resistor L is directly loaded into lower byte of program counter, lower byte of program counter, and content of resistor H, and content of resistor H is directly loaded into higher byte of program counter, into higher byte of program counter, into higher byte of program counter. And one important thing we have to note is that content of HL resistor pair will remain the same. Content of HL resistor pair is it will remain the same. Content of HL resistor pair will remain the same. So after execution of this instruction, what will be my content of PC? My content of PC will be 4050H. And what will be my content of HL? What will be my content of HL? It will be also 4050H. It will be also 4050H. It will be also 4050H. In almost all data transfer function, the content of register or the content of memory from where data is copied or fetched remains the same. Content of register or content of register pair or content of memory from where data is fetched remains the same. Remains the same. So if I talk about the length, then it is 1 byte. Then it is 1 byte instruction. Then it is 1 byte instruction. If I talk about the machine cycle, only one machine cycle. Opcode fetch is required. Opcode fetch is required because both this PC and HL is inside microprocessor only. Both this PC and HL is inside microprocessor only. If I talk about T state, then you will say, sir, that it is having only one machine cycle, opcode fetch, and opcode fetch requires 4 T states. No, here opcode fetch will require T states. Here opcode fetch will require T states. Why it is so? Why it is so? Because 16-bit data, because 16-bit data is copied, because 16-bit data is copied from HL to PC, because 16-bit data is copied from HL to PC, because 16-bit data is copied from HL to PC. So opcode fetch will require T6T state. 6T state. It is a kind of exception, you can say. It is a kind of exception. There are some other instructions also which are put into the category of exception, where opcode fetch will have 60 states, where opcode fetch will have 60 state. At the end of the instruction discussion, I will give you a list of all those instructions on a single slide, on a single slide, on a single slide. So this was all about PCSL. So this was all about PCHL. Now coming to next instruction, that is SPHL. Now coming to next instruction, that is SPHL. What it says? It says that copy H and L registers to SP register, that is stack pointer register. That is, load contents of H and L registers into the stack pointer register. Content of H register provides the higher order address, and content of L register provide low order address. It is same as that of PCHL instruction, in which content of HL register was getting copied into PC register pair, and now here content of HL register pair, and now here content of HL register pair will get copied to stack pointer register pair, to stack pointer register pair, to stack pointer register pair, to stack pointer register pair. So we should know what is this stack pointer, and if you want to know what is this stack pointer, then we should know what is stack. So we should know what is this stack pointer, and if we want to know what is the stack pointer, then we should have an idea of stack. So see, first of all, I will show you where stack pointer register pair is placed. So if this is my microprocessor, then I used to draw all the register pair, but I didn't showed you the location of stack pointer register pair. See, this I used to show you. This will be my accumulator. This will be my flag register. This is my BC register pair. This is my DE register pair. This is my HL register pair. This is my program counter. And this is my stack pointer. And this is my stack pointer. That is, stack pointer register pair is inside microprocessor. That is, stack pointer register pair is inside a microprocessor. It is inside a microprocessor. It is inside microprocessor. Now see what is a stack and what is stack pointer, and what is stack pointer. This I think is clear to you, so I can delete it. Suppose this is stack. Stack is also a kind of memory. Stack is also a kind of memory. Stack is also a kind of memory. So we can say it as stack memory. So we can say it as stack memory. Now, let's suppose we have, it is also a kind of memory. Stack memory. Stack memory, it is also a kind of memory. And suppose this is my normal memory. Suppose this is my normal memory. These are its different address location. And these are different address location of stack memory. Fine. Let's suppose these are its addresses. Here also suppose we have same addresses. Here also suppose we have same addresses. So see, what is the difference? What is the difference? This is my normal memory. This is my normal memory. This is my stack memory. This is my stack memory. In normal memory, it is filled. It is filled or it is occupied from lower address location to higher address location. Lower address location to higher address location. Suppose we have a data 3020H. Suppose we have a data 3020H, and if we want to store this data into this memory, if we want to store this data into this memory, then how it will be stored? This lower byte will be stored into lower address location. This lower byte will be stored into lower address location. This higher byte will be stored into higher address location. It will be stored into higher or address location, and the sequence of this storing of data in memory and sequence of storing this data in memory is from lower address location to higher address location. Lower address location to higher address location. Now suppose if we again want to store 10H. Now suppose we again want to store 10H, then 10H will come here. Then 10H will come at next address location. Next address location. Top to bottom approach, we can say it. Top to bottom approach. Now how this will work in stack memory? How this will work in stack memory? In stack memory, we can say stack memory as a kind of random access memory, that is read and write memory. That is read and write memory, and it is based on LIFO model, and it is based on LIFO model, that is last in first out. The data which will be stored last into the memory, it will be copied first from the memory. Data which is stored last in the memory will be copied first into the memory. So see how it will work. In stack memory, first higher higher address locations are filled first, and then lower address location are filled, and then lower address location are filled. That is, suppose again if we want to copy this data into stack memory, if we want to copy this data into stack memory, then how it will be filled? This 30H will come at 3004H address location, and this 20H will come as at 3003H address location. See, here also our memory rule is applying. See, here also our memory rule is applying. This higher byte is copied at higher address location, and this lower byte is copied at lower address location. But the thing is that in this, the order of filling data is like this. That is bottom to top approach. That is bottom to top approach. First, the higher address location are filled. First, higher address location are filled, and then lower address location are filled. Then lower address location are filled. Now, if we want to store 10H also into the stack memory, now if we want to copy 10H also into the memory, then 10H will come here. Then 10H will come here. Now if we want to fetch data from stack memory, now if we want to fetch data from stack memory, then this 10H will be fetched first. This 10H will be fetched first. this 10H will be fetched first, then 20H will be fetched, then 20H will be fetched, then 30H will be fetched. That's why I told you that stack memory is based on LIFO model, that the data which is saved last will be taken out first. Data which is saved last will be taken out first. But here in this normal memory, it is based upon FIFO model. It is based upon FIFO model, that is first in, first out. First in, first out. This data was copied into the memory first. So while fetching also, this will be fetched first. This will be fetched first. This will be fetched first. Fine. Now if we come to the stack pointer, what is the role of stack pointer? So stack pointer is defined as it points to data. It points to data at the top of stack. It points to data at the top of stack. So stack memory points data at the top of stack, stack pointer. So stack pointer points data at the top of the stack. Now see, which data is at top of the stack? 10H. 10H data is top of the stack, because if we want to store some more data in the stack memory, then where it will come? It will come above 10H. It will come above 10H. So at this time, 10H data is at top of the stack. And what is the address location? 3002H. 3002H. So this 3002H is my stack pointer, is my stack pointer, is my stack pointer, because stack pointer points data at top of the stack. Stack pointer is a kind of address location. Stack pointer is itself a address location. Stack pointer is itself a address location which points data at top of the stack memory, which points data at top of the stack memory. Now suppose one more data. Now suppose one more data 15H is there, and we want to copy it into stack memory. Then where this 15H will come? It will come here. It will come here. So now where will my stack pointer go? My stack pointer is a dynamic thing. My stack pointer is a dynamic thing which will keep changing its value, which will keep changing its value or location as data is copied or removed from stack memory, as data is copied or removed from stack memory. So now we have added one more data 15H into stack memory. So my stack pointer, so my stack pointer will shift here. So my stack pointer will shift here, because now 15H, because now 15H is data at the top of the stack. Now 15H is data at the top of the stack. Now suppose if I take it SP1, if I take it SP1 and this is SP. Now suppose we have removed this data, we have removed this data. So again my stack pointer will come here, my stack pointer will come here. Now suppose we have removed this data also. Now suppose we have removed this data also. So my stack pointer will come here. So my stack pointer will come here. Let it denote it as SP2. Let it denote it as SP2. So if I talk about SP1 and SP2 in respect of SP, then see what is my SP1? my SP1 is SP minus 1. See, 3002H and minus 1 will become 3001H. If I talk about SP2, then what is my SP2? SP2 is SP plus 1. SP plus 1. See my SP2, see my SP 3002 and my SP2 3003H means 3002 plus 1. Why it is so? Why it is so? Because in stack pointer we are filling data from bottom to top. From bottom to top. That is from higher address to lower address. From higher address to lower address. So from this and this, from SP1 and SP2, we will conclude one very important thing which will be used in many important instructions like push, pop, and exchange instruction also, which we will look shortly. We will conclude a very important uh, concept here concept here concept here, that is, whenever a data, whenever, suppose here, now suppose here is my stack pointer, suppose here is my stack pointer, this is not present right now, suppose consider it, suppose here is my stack pointer and this is the data at top of the stack. So now if we will add data into stack memory, then content of stack pointer will be decremented by 1. It will be decremented by 1. And suppose this is my data at top of the stack, ignore this, and if we will fetch this data or remove this data, then my stack pointer will be incremented by 1. Then my stack pointer will be incremented by 1. Then my stack pointer will be incremented by 1. That is, suppose if it is asked in exam, that my stack pointer is suppose 3005H, and it is said to you that 16 by, that is 16 bit data is copied, that is 16 bit data is copied in stack memory. 16-bit data is copied in stack memory. Then what will be my value of stack pointer? What will be my value of stack pointer? Then we know that 8-bit data, that is 1 byte data, is copied at one address location, and we already know that 8-bit of 1 byte data is copied at one address location. So to copy 16-bit data, or 2 byte data, two address location will be required. That is my new stack pointer. Will be decremented by 2. That is, it will be decremented by 2 and it will become 3003H. It will become 3003H. It will be decremented by 2 because see, this is my stack pointer. Suppose my stack pointer, this is my stack memory. Suppose this is my here is my stack pointer with address location this, data something is 10H here. Now if we want to copy 16-bit data, that is, suppose this is XX and YY, then where my address will go, it will be decremented because it is from bottom to top, from higher address to lower address. So it will be 3004 and 3003. So my stack pointer will come here. So we can see that my stack pointer is decremented by 2. It is decremented by 2. Now suppose in the same question, if it is said that instead of copying, if it will say that 16-bit data is fetched from stack memory, then what will be my new stack pointer? My new stack pointer will be incremented by 2. My new stack pointer will be incremented. My new stack pointer will be incremented by 2. It will be incremented by 2. It will be incremented. It will be incremented by 2. Suppose we extend it. Suppose we extend it. And suppose this all are not there. Suppose this all are not there. Now if we are, suppose this is 20h and it is 30h, 3006 3007. Now if we will fetch this data, where my stack pointer will come, it will come here, that is at address location 300h, 3007h, 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 3007h. So it will be incremented. So it will be incremented by 2. It will be incremented by 2. So I hope now the concept of this stack memory, concept of this stack pointer is clear to you. Now coming to SPHL. It is very simple. Suppose my content of stack pointer register is 2010h and my content of HL register pair is 4050h. After execution of this instruction, what will be my value of stack pointer? My value of stack pointer will become 4050h. And what will be my value of HL? It will remain 4050h. It will remain 4050h. So if I talk about the length, then it is also 1 byte. If I talk about machine cycle, it also has one machine cycle, that is opcode fetch. If I talk about T state, then it will also have 6 T states. For opcode fetch, it will also have 6 T states because 16-bit data is copied. So it is also in category of exception. So it is also in category of exception. So this is also in category of this. What we say is that exception. Now coming to next instruction. So it is exchange HL and DE. It is same. We are exchanging data. Here we are exchanging data between HL and DE. Here we are exchanging data. Here we are exchanging data. Between HL and DE. That is, contents of H registers are exchanged with contents of register D, and contents of register L are exchanged with contents of register E. Suppose we have HL register pair. Its content is 4050H, and we have DE register pair and its content is 2010H. So after execution of this instruction XCHG, what will be content of HL register? Its content will be 2010H. And what will be content of DE register? And what will be content of DE register? What will be content of DE register? It will be 4050H. That is, content of DE register will be copied to HL register, and content of HL register will be copied to DE register pair. That is, exchange of data is taking place. So after execution of this instruction, content of both HL register pair and DE register pair will change. That is after execution of this instruction. that is after execution of this instruction, content of both HL and DE register pair, will change. It will change. Fine. Now if we talk about length, it is also 1 byte instruction. If we talk about machine code, it will also have only one machine code, that is opcode fetch, because both HL and DE is inside microprocessor only. If I talk about T state, then for opcode fetch, it will have 4 T states. For opcode fetch, it will have 4 T states. Now, coming to next instruction, XTHL. XTHL. What is the meaning of this? Exchange HL with top of stack. Exchange HL with top of stack. That is, content of L register are exchanged with stack location pointed by contents of stack pointer register. Contents of H registers are exchanged with next stack location. It is exchanged with next stack location SP plus 1. Content of stack pointer are not altered. So what is its meaning? Suppose we have a HL register pair. Whose content is 4050H. And here we are having a stack memory. Fine. Suppose here we are having data 20H, here we are having data 10H, and this address location is 3003H, suppose. So this will be one increment of this, so it will be 3004H. Fine. So say see here, what is the data at the top of the stack? What is the data at the top of the stack? What is the data at the top of the stack? What is the data at the top of the stack? This is the data at top of the stack. What is its memory location? It is 3003H. So what will be my stack pointer, or where will be my stack pointer? My stack pointer will be here only. Because it points data at top of the stack. And what is the content of stack pointer? Its content will be 3003H. Now see, after execution of this instruction, what will happen? This 50H will come here. And this 20H will come here. This 20H will be copied into the lower byte register, that is L register, and this 50H will be copied into lower address line, or lower address location. And this 40H will come here. This 40H will come here. And this 10H will come here. This 10H will come here. So this way the exchange will take place. That's only written here. That is, content of L register are exchanged with data with stack location pointed by content of stack pointer register. Fine. This is pointed by stack pointer location. So this data will come here because this is lower address. And content of H register are exchanged with next stack location, that is SP plus 1. And this data will be copied here, and it will be an increment of this address location, one increment of this address location. So it will be 3004H. Now see, after this exchange, will my content of stack pointer change? See, after this exchange, will my content of stack pointer change? No, it will not change, because now the data which will be at the top of the stack will be 50h, it will not be 20h, but it will be 50h. But still, what is the address location of data at top of the stack? It is still 3003h, so my stack pointer content will also be the same, because it points to data at top of the stack, no matter what is the data. Sometimes it may be AB, sometimes it may be CD, but it is only dependent upon the location or its position. Its position is not changing. If its position would have shifted upwards or its position would have shifted downwards, then its content would have changed. Then its content would have changed. Now see how it will function. Here we are having registers. PC, stack pointer, instruction decoder, ALU, CU. Here is temporary register WZ. This is my microprocessor, and suppose this is my stack memory. And here we are having 3003H, 3004H, 3005H, 3006H. Here data is 20H, here data is 30H. Stack pointer is here, because this is the data at the top of the stack. Now see how this will be executed. We have to draw one more memory here, or we can modify this only, Suppose this is my memory. I will call it first a memory. See this 3000H, 3001H, 3002H, and here we can say that it is 3007H, 3008H, 3009H, 300AH. After 9, A comes in hexadecimal. Suppose here data is 10H, data is 20H. See, this one is my normal memory. And this one is my stack memory. That is, here the data will be copied into the memory from lower address location to higher address location, and here the data will be copied into memory. Here data will be copied in this direction. Here data will be copied in this direction. Suppose we have a notebook. And we have a habit of starting one subject from starting of the notebook, and we have a habit of starting another subject from the back side of the same notebook, from the back side of the same notebook, from the back side of the same notebook, from the back side of the same notebook. So suppose you are attending two simultaneous classes in a day, so you will take with yourself one notebook and you will start writing contents of first subject from starting of the notebook, and it will be in this manner, top to bottom, and you will start writing the second subject from the back side of the notebook, and that will be in this direction, that will be in this direction, that will be in this direction. So fine, and suppose this subject is also completed, this subject is also completed, and you want to differentiate both this subject through a pointer. You want to differentiate both this subject through a pointer so that you can easily open and study it. So you will use a stack pointer, that is, you will use some sort of flag, and you will put flag in between them, and which will differentiate normal memory and stack memory. Now suppose 1-2 pages is added more in this subject, then my stack pointer will move upwards, and suppose 1-2 pages is deleted from this subject, then my stack pointer will move downward. So this will be my basic funda. So see, if we have an instruction like this, 3000H XTHL, then see how it will be executed. First, the programmer will copy, or it will feed opcode into the memory. It will feed opcode into the memory. So it will occupy one memory location or 1 byte location. So its length is 1 byte. So its length is 1 byte. Fine. Now after that, reset button will be pressed. Reset button will be pressed. Reset button will be pressed. Now microprocessor will first fetch this opcode. Microprocessor will first fetch this opcode and decode it. After decoding, it's know that it is XTHL extraction, that is content of HL, that is content of HL has to be exchanged with content of stack memory. It has to be exchanged with content of stack memory. So see how it will be done. Microprocessor will send address 3007H through address bus into this stack memory. This memory location will be highlighted. Now microprocessor will send memory read control signal. It will send memory read control signal. Now this data will be fetched. And it will be brought back into the microprocessor through data line. Now say, will it be copied into L? No, it will not be directly copied into L. Otherwise, the content of L will get removed. But we don't want this content to get removed, because the same content has to be copied here also. So what will happen? This 10s data will come into the temporary register pair, and it will be saved here. Now what microprocessor will do? Microprocessor will send memory write control signal. And now data of L will be copied here. Suppose HL has content 10 not 10. Suppose HL has content 4050H. So now microprocessor will send memory read control signal. Microprocessor will now send memory write control signal. And the content of L register will get copied here. content of L register will get copied here. Fine. So this data, 10s data, and simultaneously this data will now get copied into register L. Now this data will now get copied into register L because the content of register L, because the previous content of register L is already copied in the stack memory. So there is no fear or no chance of data getting deleted. So after this instruction, after this execution, what will happen? This 10H data is copied into register L is copied into register L through temporary register and this data content of register L is copied into stack memory Now what will happen? Now microprocessor will send another address 3008H through address bus. So now this address location will get highlighted. Now microprocessor will send memory read control signal. Now this data, 20H data will be copied, or it will be fetched, and it will be brought back into the microprocessor. Now whether it will be copied into register L, H, no, because otherwise the content of register H will get deleted. But we want content of register H to be remained because we have to copy same content here. So this 20H will come into temporary register. Now microprocessor will again send memory write control signal. Now the content of H register, will be copied here. And simultaneously this 20H will get copied here. So now what will be the content of HL register pair? It will be 2010H. And what is the content of the top two location of stack pointer? It will be 50H, 40H. Now see, will my value of stack pointer change? No, my value of stack pointer will not change. So if I talk about the machine cycles, what are the machine cycles? Machine cycles are opcode fetch. To fetch this opcode of XTHL. Then the next one will be memory read. To fetch this data. Then it will be memory write. To copy content of register L. At this address location. Now what will happen? Now the next machine cycle will be memory read, because now we want to fetch this data. And the next machine cycle will again be memory write. Because we want to write content of H register at this address location. So total machine cycle is 1, 2, 3, 4, 5. Total machine cycle is 5. And what is my sequence? My sequence is first opcode fetch. Then we will have memory read. Then we will have memory write. Then we will have memory read. And then we will have memory write. You should know this sequence, because most of the time we have seen that memory read comes first, then memory write comes. But here memory read, memory write are in between only. So you should know this sequence because it may come in the exam. So what will be the total number of T states? It will be 40, 3T, 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 3T. 7, 10, 13, 16. 16 T states are required here. 16 T states are required here. So very important instruction this one. Very important instruction this one. So now I think you must be having the concept of stack pointer, stack memory, and how this function is implemented and how this instruction is implemented.